All right, everybody, welcome to the Propeller meeting for August 12th. Um, Glad to see you guys here. I have a few things to talk about. Stephen can answer any questions that you might have about his AI stuff. Well, probably shouldn't call it that, but the documentation effort he's been undertaking to document all the tech details of the P2 so that people could program it better, especially with the assistance of AI. Does anyone have anything they want to say first? Oh, Paul's here. Good to see you. All right. I could talk briefly about this HDMI board I've been working on. It's been kind of uh, difficult. I don't really know. It's these little tiny switcher chips are so delicate. I've had to replace like four of them, and then after a while, the replacement didn't do anything. So I had to get rid of that anyway and move to a linear regulator. I'll share and show the board here. Let's see. Let's see. How do I do that? I guess I'll go content only and share my screen. Okay. Can you guys see the circuit board?
Yep.
Yep.
Okay,
Okay,
good.
good.
So
So
this
this
here
here
is,
is,
oh, wait, now I have this crazy echo. Wait, now it's gone. Okay. This is this MS9288 C chip from Macro Silicon in China. It does this job of taking analog VGA signals plus left and right audio and then converting them into HDMI so they can come out of, one of these HDMI connectors. And the P2, of course, can generate these same signals, but we can't go fast enough to do 1080p because it has to signal at 10 times 148.5 megahertz, which is like 1.5 gigahertz. And the 180 nanometer process that the P2 is built in just cannot switch that fast. So, um, I've been using this chip to convert what the P2 can generate fine, which is analog 1080p, and then create the HDMI. And what's really nice about this setup is that we get to pack in the left and right audio channels too, so we don't need any extra cabling. If you want to have sound, it goes right to the TV. Um, the problem I was having initially, which was just really, I mean, it's simple in the end, but right here you see this is a linear regulator. On the original board, I had put a switcher, and the switcher has these characteristics where it's oscillating. Of course, it's yanking on this coil and it's causing some ground noise, which might have been maybe tolerable if it was a fixed frequency. We could have dealt with it. But the trouble is the switcher runs in spurts. Like it's like, oh, we're low on voltage, so start pumping it up. Boop, 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 boop. So it like fires off a bunch of pulses on the switcher, and then that creates a big power draw or current draw on ground and 5 volts, but has the effect of lifting up the local ground on this board that's out in a connector, and it shifts it away from the reference ground that the P2 edge had, right? Because P2 edge has its own local ground, which is very low impedance. And within that little context, it was generating perfectly registered signals against ground. Well, when they get out to this board and ground is bouncing around, your signals, here's my RGB signals, right? They might be stable, but the ground's going like this, and the ADC is referenced to ground. So it appears on the board that this is happening, right? It's relative. So this was creating all these striations in the background, especially when he had like, you know, it was worse seemingly around half color, like if you did a half intensity white. Didn't work. It didn't affect blue for some reason, but the red and green channels were horrible. So that was not going to be remedied, I think, by any type of filtration because it was just too disruptive. And you could actually take the scope probe and touch it on the P2 edge and look at its ground. Clip the lead to the P2 edge, the ground clip, then take the probe and touch it to ground, and you'll see an amount of noise. Then you take the probe out to this little card plugged in near, and it's like way bigger. So it's very obvious that the ground was moving around, and that was the source of disruption of the signals because they have to go into the ADC in this thing, and they get digitized at 148 megahertz, and then they get turned into this HDMI stream. So all that signal path has to be good because your eyes are pretty sensitive, just like your ears are. And if unless you have quiet electronics, it's going to look or sound terrible. So I've put now a little linear regulator, this thing over here on, and stapled it down to kind of help spread the heat. The back of the board looks like this. I also put a lot of vias underneath the HDMI converter chip to kind of help wick heat away because this thing's running pretty hot. I mean, this board, that that converter chip runs hot, but now that I've had to add this, linear regulator running for at 3.3, making 1.8 volts output for this guy, this is going to generate as much heat again as this thing does. So I've been more careful about at least utilizing what we have for copper area and putting more copper on the board. And I think this one will work better, but it's probably just going to run really hot. But the only way to get around that is to make a much larger board, which I could do, but I just want to have something that's like proof of concepts. I've got a good stable video circuit that I can use to do other kinds of development with. Any questions? I'll see if I can pull the 3D thing up here. Let's see. This thing has this. I don't know if I have all the models in here properly, but it's kind of tough to remember where they were and to drag them all forward when you move things.
I guess the other trick could be to use what they do on the eval board. I think it was the eval board. I don't remember now, but they bring the 5 volt down to 3.65 and then use a LDO to bring that to 3.3. Yeah.
Yeah, yeah. I was talking to ChatGPT. It actually does have a lot of good ideas, and it was saying that we could do that, but I think any switcher at all is going to cause this horrendous ground bounce because the current flow is uneven, and it could be filtered maybe somewhat, but I don't know. I just used a pure straight up, I'm going to drive it off the 3.3 volt thing, which is here. So it's going to run cooler than if I were running it off of 5 volts, but it's still going to get hot. But this is like, smooth flowing plumbing now. There's no crazy interrupter doing some kind of PWM stuff on us. So it should be quiet. But here's a little board. See, it's
I
a
guess the
lot.
thing here is this board is so small. I think the somebody posted an image of one of the commercial ones that's, it's not huge, but it's probably like
Yeah.
twice this big. So
Oh, yeah, they're substantially bigger. That converter chip does need a lot of area because it generates just a lot of heat. And this board can't get rid of it. I suppose having the cable plugged in helps a lot. It can send some of the heat up through these pins and into the shell. But it's hot. You put your finger on the bottom of that and it kind of hurts.
oh, I hadn't thought about the connector taking heat, but yeah, you're right. That's a lot of wires and the ground, big ground. Yeah, that should do it.
Yeah. So I put, as much copper as I could down. I flooded both the top and the bottom. And on the top, what I did, which I was kind of reluctant to do, is I didn't use thermal reliefs. Like, let's see, let me let me tell it to redraw without the components. Uh, yeah, display components. Turn that off. Redraw. So I've had bad experiences with this, not electrically bad experiences, but assembly experiences. So you see now I have no thermal reliefs, right? Because in a tight layout like this, it really can't get in enough spokes to do it right. So it's better if you just flood everything and let the copper, go everywhere, and then it has solder mask openings for where there are going to be components. But when you like solder on this capacitor here, you're going to have to basically, this is copper, so it's very heat conducting. So you're going to have to, heat up everything else around here to get that solder to wet. But electrically, it's going to be just fine. See, I did that here too. This is where one of the pins of the header goes. So electrically, it's really good, but it can be difficult to make. But what I found was you cannot work this with a normal soldering iron. It's impossible. The tip can't be small enough. You can't get underneath this thing, because these pins, I mean, they're only exposing like a little edge of this pad because the lands sit on those things or the feet on the bottom of the chip, and there's just hardly anything sticking out, especially when you get to like these kind of chips. Like let me turn the parts back on. You just can't get down in there. Boy, this computer's really so I bought the cheapest laptop I could just to because all my laptops get destroyed. They eventually wind up in the kids' hands and they get dog-eared and then they're just out of commission. So I bought a cheapie. Anyway, you see this thing here. You see those little pins in there. Can't get to that. And this is a very tall part right here. So you can't get a soldering iron in there. But what I did is I found on Amazon, you can get these, the soldering pen, the air pencils. You can get these really, I got this great one. It was like $47. And you just pick it up and it has like a little, I guess, an accelerometer in it. So it knows when you're pointing the nozzle down. Then it turns the fan on, turns the heater on, and then and it has a little digital readout. You dial up the set point you want. And, or yeah, I think it has some up down buttons or whatever. But anyway, it just goes brrr, goes up to the set point and sits there. And the heater and the fan are in the hand unit. So it's not like you have a central pump in a box that's then blowing air through a hose. That's how these things used to be built. Well, this is really smart. It's all super compact. Everything's at the point of load. Anyway, this little thing, I turn it down to the lowest airflow possible. I put it on 590 Fahrenheit, and I got a little syringe of flux. It's uh it's like what they show in these short little like maybe TikTok videos of reworking cell phones. You see them squirt this rosin flux onto the board, and then once the heat hits it, it just sheets out. And that stuff works awesome. So I mean, one syringe of this stuff can run forever. And anyway, I just put a little dab of that on and then take that hot air pencil and, kind of just, if I'm going around the chip, I'll have to kind of make a circular pattern. But if I'm doing a small part, just hang over that. Then I have some super fine tweezers, right? And this process is so stress-free on what you're working on that I've replaced this chip, this big one here, like 4 times on the same circuit board because I kept experimenting with, you know, different switchers and they kept blowing it out. So I had to keep replacing it and it was no problem at all. I mean, I could heat that thing up. There's a little surface tension because there's a big old ground pad underneath that, but I could just get that thing off the board. It would stick a little bit because of the surface tension, but I could pull it up and then hot air level it and then maybe go over it at that point with a little fine tip iron just to make sure I've got a good amount of solder on every little pad. Then set the new chip down, or then I'd put more flux on, kind of reflow it again, set the chip down, and then spend more time to get it to really reflow. And it worked beautifully. I mean, there was like no wear on the circuit board at all. I could just replace parts indefinitely without any wear on the board.
Oh, so I do something similar, but instead of using solder paste, I tried that. That wasn't all that great. What I do instead is I just solder the pads
Yeah,
and then
that's what I did.
put flux on top, and then that works just as well.
Yeah, I think it works better because, trying to dole out little minute uh, amounts of solder flux or paste is too much trouble. So what I do is get the board all fluxed over, get a little blob of solder on the end of an iron, and just kind of spend the time to drag that slowly over everything, and it deposits the solder everywhere you're going to need it. And then, reflux it, hot air level it again, then put the parts down and just more hot air and they go. And I think I was telling you last time the 0402s were a pain, but you said they were easy. I found actually they were very easy. You get them situated, get the air on them. As long as they're not like getting blown off the board, I got to run the air as slow as I can get it. But when I do that, they just,
Yeah,
surface tension
yeah, they're
grabs
easy.
them. Yeah, they're really not hard. I
And I
would
wound
even
up having to do it a lot because they tombstone a lot on me. So I wound up having to hot air them, knock them down
uh
a lot.
yeah, yes. I actually didn't have tombstone. I had them like twisting on me, so I had to use the super fine tweezer tips to kind of get them back into position, but uh then everything soldered beautifully. But you know what we need?
Oh, oh, not this way. I mean, when I put stuff in the oven, that's when they
Oh, the
tombstone.
oven. Yeah, yeah. I was reading about that, and apparently you got to have capacitors are more difficult than resistors, so you need like a different amount of base on the pad for a cap than a resistor. It's just slightly different because of the geometries. But yeah, you can control tombstoning a bit by pad shape.
Well, it's just the
But
P2 layout that kind of like that I copied from your guys' board. It has like a gazillion capacitors, and like there's always going to be a couple that tombstone. So just, I don't think it's
oh
a,
yeah, I see. Yeah, yeah, maybe you can't stop it. Yeah, but anyway, I'm really pleased. This hot air. I need a soldering iron to put the solder down originally, where it's going to need to be. But after that, it's all just the hot air thing. And at 47 bucks, it's all digitally controlled. It's like awesome. Those things used to cost like 500 bucks, but now, the Chinese are making them and they're sufficient for what we need, and they're very cheap.
yeah. I got I have the old kind that you're talking about, and I have the new kind. And one of the new ones died on me, and I tried to get a replacement. You can't buy a new.
No.
You can't. I guess a replacement thing is costs more than the whole thing costs to begin with. So
Oh yeah. Well, 47 bucks for the whole tool, that's like the base, the cabling, all the tool that goes in your hand, and it's so cheap. I just toss it and get another one.
What's the big chip?
That's the MS9288C. That's by Macro Silicon. Let's see. I have a schematic here. Just a minute. Wait, here it is. It is this thing right here. So it's a 48 pin part, and see, this is H sync in, V sync in, red in, green in, blue in, and then analog, audio left, audio right. And then you just got to give it all this conditioned power. It takes 1.8 and 3.3 volts. And then it talks to this thing here, which is the HDMI connector, right? So it generates all these differential signal pairs for the HDMI, and then it does all this other stuff like the I squared C thing for negotiating like what kind of modes are available. But the thing is, this is a Chinese product, and they give you enough in the data sheet to build a VGA to HDMI converter, but the chip has some firmware in it, and it does recognize some limited number of modes. It'll do like 640 by 480 and a bunch of other stuff, but it has a lot of registers in it, but they kind of keep that confidential. You don't know. They have another one that you actually could program, but it was looking so complicated that I figured let's just get this small one. We'll just output VGA because it's most efficient at the pin level anyway. Although component video, they have a component to HDMI chip, but it's one of the kind of things where you have to get into and program it a little bit, and it was just way too complicated. It's a bigger, more expensive chip. So for two more pins, we can add H sync and V sync rather than have the syncs on the green. Well, the H syncs were on every gun on R, G, and B, but I think the green also had the V sync for Y, P, B, P, R, or component video. But we'll just use VGA. It's simple, we can get this cheaper, kind of out of the box, off the shelf part that just does the job, and then we'll
yeah,
just do it
I
that
had a
way.
question about how easy is it to get that chip? Because I don't think you can find it on like DigiKey or Mauser. You have to
No.
get it. You have to get it some other way.
If you look, there's one distributor that also sells like the PS RAM chips. They're called LSC or something. You can buy it through them, but I had to contact them. The way I went is I contacted them in China, and then you have to kind of like open a dialogue with them. and then they have a minimum order quantity. And I think we had to buy like 25 chips for $60. It was no big deal at all, but and then they're like 85 cents in volume. They're not expensive. But you have to kind of, they want to have like they want to know who you are and what you're going to do with it. And then once you do an NDA, I think I had to do an NDA. Then they sent us the reference schematic, which is basically just the same thing I've got here. So you take a lot of your power and you run it through like a bead and then a 22 microfarad and a point 0.1 to make like, filtration for those analog supplies. And then for stuff like, and then this is the funny stuff that goes on with that SCO SDA, the I squared C thing that works over the HDMI port. Then there's a couple reference components. You need a 0.1 cap for a filter, and then you need a 1K resistor for, um, I don't know, I think that's a reference for the audio circuit. It has like a 24-bit ADC for audio, and then it has 10-bit 165 megahertz ADCs for the RG and B signals. So it's better than 8 bits, but I kind of need a couple bits of headroom just to make sure stuff comes through the system without having like, you know, different looking shades when the intention was that they be the same. So I don't think your eye can't really see past 8 bits of resolution. It can if you have a whole screen or your half of a screen is one, half is the other, you can see the difference, but up, in things that are proximate, you can't really tell the difference. So this was the connector.
Yeah,
And this is that.
the chip is weird. The companies are very sketchy about HDMI stuff, and it has to do with the encryption ability. Like this, I guess, doesn't
Oh
have
yeah,
encryption, or at least they don't. They probably don't mention it if they did have it. But
I don't think it does. I'm
and
sure it doesn't.
it's weird that it doesn't have US. I wonder if there's some like if they're not abiding by some legality concerning HDMI.
It
That
could be. It could be. But you know how we found this chip, right? It was in if you go to Amazon and you buy like a VGA to HDMI or a component to HDMI converter, you open it up and this is the chip sitting in there, especially for the VGA one. The component to HDMI would have used a slightly bigger, slightly more expensive chip. But macro silicon parts are in all those converters and they're like maybe $10, right? With the cables and everything. But our cost on building this is probably going to be like 12 or 15 just because we're not in Asia and we just everything's more here. But basically it's just oh, and check this out.
Is
This
that
is
is that chip making a lot of heat?
Yeah, it's pretty hot. It runs hot, but it's got those 10-bit flash ADCs that run up to 165 megahertz. There's 3 of those for the RG and B channels. And it's just I understand why it would run hot, but it is pretty hot. Check this out here. This is a kind of a cool thing. See, when we bring our red signal in, we terminate it, the red, green, and blue, right? We terminate them with 75 ohms, and that kind of, I think, forms a transmission line. So, but then what we do is we capacitively couple it into the chip. So there's going to be a problem in a system where you're going to have different ground potentials, right? So what this does is this allows the chip internally to look at the black period and figure out what the black level is by the voltage level, post cap. Then it can properly interpret all voltages above ground, above zero, this kind of virtual zero, and wind up not having some like, white offset or something. Does that make sense what I said? Because there's going to be a difference between this ground potential and probably where the signals are coming from. But this takes care of it. You bring it in capacitively. Now you don't care what the DC offset is, but you record like what was it during syncing and blanking. That's our black level. Then anything above that's going to be on somewhat.
Oh, well,
So
that's
that's
an interesting point. Like, I wonder if you DC coupled from the prop chip, yeah, AC coupled, I mean, through a cap, if that would have stopped that. Oh, I guess that noise is on the video frequency though, so I guess it wouldn't have stopped anything. Yeah.
yeah, no, it wouldn't. This little scheme here simply takes care of a ground potential offset between the signal generator and then the converter because there's gonna be one. You just can't get around it. Especially if you're drawing, there's a current loop from your source system coming back. It's going to have the tendency to lift ground a little bit if current's flowing from something they're supplying you back to ground. Ground's going to come up some millivolts, and that's going to create like a black offset or a white offset, or anyway, you're going to be off.
Oh, I just remembered a question I had for you. Do you see any reason this wouldn't work on P1? I think it will, but I was wondering what you think.
It would work, but for P1 and VGA, um, we only have because we have eight. Well, no, we can output more than 8 bits, right? I just made it. I made it do horizontal, vertical, and then 2 bits for R, 2 bits for G, 2 bits for. So I had 4 levels of red, green, and blue, and then H sync and V sync. So this would totally work with that. Yeah, you would just have coarser steps, because whereas the P2 has like a nice 8-bit DAC in every pin, so it can draw really nice graphics very quickly. Whereas the P1 is kind of doing it digitally and then using resistors to mix the states down to get a few levels. Because ultimately all that's coming in here, so you can see on this thing here, we have red, green, blue, and H sync, and those are a group of DAC signals because H sync is it's tied exactly to the timing of the pixels, right? Whereas V sync you can control through software. It doesn't have any like all that matters is was it high or low before the H sync occurred. So you can software control V sync, but H sync, when you draw the video line, it has to be exactly time coordinated with the red, green, and blue signals. So anyway, we had red, green, blue, H sync. Here's V sync on 8. And then over here, this was like an extra pin because right and left audio are up on these pins. But this pin goes back. Let's see, where's this control thing? I think it's here. Yeah, it goes to this thing called CEC on the HDMI connector, which is, I don't remember what it stands for, but basically it's some kind of low baud communication thing with the TV where you can detect did it get turned on, turned off, did a remote control give some kind of it's like for spreading awareness of I think basically IR remotes or what start out as IR remotes and the TV can send back to you what happened so you could witness it. So we pull it up
Yeah,
with
I
a
mean
22K.
that has some interesting things you could do there, right? So I mean, if your TV, if you hit a button that your TV, if you hit a button on the remote that the TV doesn't respond to, but you can capture it this way, you
Yeah.
could make the P2 like do certain things with the remote. But yeah, I thought about that. I can't really think of any use for it, but I mean, I'm sure there is something.
It's something. Yeah. I was playing around with well, I had this thing working, and then it kept breaking. And I think at one point it just wasn't working right, and the TV thought that it wasn't powered up, and I was sort of probing it. I had like this little eye loop, and I'm down there with the little scope probe, and I'm going along the connectors. Let's see, can I get this? I was probing these things here, and I saw a little arc between these two pins. And I think I might have blown up some trace on the circuit because that's 5 volts and that's ground and that's hot plug detect or plug detect. Anyway, maybe I wrecked my board because I wound up replacing the switcher a few times and I couldn't get it working again, but I couldn't find an open anywhere. It's like it's too dumb to fail, but it failed. But those switchers, they're just so persnickety and temperamental. I'm just going to be glad to deal with this dumb linear regulator.
Yeah, I mean, I don't know why you made the board so small, but I guess to make it, I guess it's interesting being small, but I guess when it's that small, I guess maybe that's you just run up against you have no choice but to use linear regulator.
Yeah. See, if I could build what I want to eventually do is make a P2 board with the P2 on it and then separate 5 volt, probably 3.8, maybe 3.3 volt switchers. 3.8 we can use LDOs to get a nice 3.3 for analog, very quiet 3.3. But anyway, and also a 1.8 volt switcher. So I simply wouldn't need this regulator. I'd already have all the power supply voltages I need. I just locally condition them with like pi filters and then run them into the chip here for power.
How many amps are you needing?
So at 1.8 volt, this thing consumes 220 milliamps. And now I'm going to regulate that with this linear regulator here. So it's going to take 220 more milliamps at 3.3 volts, whereas it was only taking like 80 milliamps at 5 volts, right? Because the switcher is like 90 something percent efficient. So it was, a third the voltage is a third. How does this work? Yeah, you see a third the current on the supply end. So, but now this takes 80 milliamps at 3.3, just on the 3.3 rails, and its 1.8 rails take 220. So it's going to take about 300 milliamps of 3.3 volt source to drive this chip. And the edge, I think, is good for like 500 milliamps per 8 pins.
Oh wait,
So
why did you say? Because I thought, wait a minute, I think it's because
remember
you wait. I think so. You said the chip used 220 milliamps. I thought.
at 1.8 volts, yeah. But
Oh,
see if if
there's other
we're
supplies. Okay, to take.
Yeah, it takes 3.3 and 1.8. So at the 1.8 volt supply, it takes 220 milliamps. But if we're running a switcher off of 5 volts, that's only 80 milliamps at 5 volts, right? Because the voltage goes down, current goes up. But with an LD with a linear regulator like I put on here now, because I can't handle all that pounding on ground, it's going to always burn 220 milliamps at 3.3 volts, and it's just going to the difference. What's 3.3 minus 1.8? Is that 1.5? It's just going to, you know, it's going to be 1.5 volts times 220 milliamps. What's that? 330 milliwatts. It's gonna do like a third of a watt.
Yeah, so in cases like that, I'm always tempted to try to use a series transistor and see if I can get away with a smaller size LDO. But I've never done that. But
Uh,
I suppose you.
this LDO here, I picked it because there are parts that don't have any ground pads that they say will do this current, but they're going to get so hot. I just don't believe it would be a good idea. So I picked this one because see, it has a whole ground pad underneath it, and I've got it going to this copper here, and I've got it stapled down to try to heat pipe it downward. So hopefully I can take the heat off that chip. It's going to heat the board up, but I don't want to drive the chip into thermal shutdown.
Yeah, I guess the ultimate thing is you don't want to have to put warning, danger, hot, don't touch on the board, right? So that's like, which I guess it's the only thing to stay away from.
Yeah, it won't permanently harm anybody. I mean, there are plenty of electronic things that run pretty hot out there, but it is hot. I mean, if I just made the board way bigger, it would cool it down a bit. There'd be more radiating area, but the connector probably helps. Also, let's see. I think these probably help a little bit. This should kind of transfer some of that heat into those pins. Not a whole lot, but something. Um,
Have you
anyway,
done any simulation in LT Spice or anything like that? I've played a
yeah.
lot. I played a lot with the with switchers and trying to
Uh,
solve problems. So I might actually be able to, I don't know, do some tricks. But I need something to start with. Like what I need to have an equivalent circuit that I can
Hmm.
okay.
I put the schematic on the thread. You know the P2 forum or the Propeller forum? There's
Yeah.
a Propeller 2 subsection. I posted the schematic in there. And I think that, the only way we could make a switcher work is if we got a constant PWMing switcher that would gradually like throttle up and down. Whereas this thing runs in these like unit burst modes and it creates noise that you just can't filter out. It's like it draws hard, then releases. Then when it needs to, it draws hard again. And the frequency, the period of that is all over the place and it's very low. It's like, a couple microseconds, even though the switcher, when it runs at 4 megahertz.
Well, um, what one of the solutions that I've come up with recently is just a supercapacitor because um,
Oh yeah.
they've come down a lot in price. You can get a 1 farad supercapacitor for less than $1, and
Wow.
if you go up to like 10 or something like that, then the resistance is so low that it's practically negligible, and then so that because that's the use case for the supercapacitor is bursty kind of
Yeah,
um,
yeah. And you
apart.
want it to have super low ESR, right?
Yes,
Yeah.
and
So
as long as you have your path to and from the capacitor and the chip that's drinking that, it has to either have a twisted pair or it has to have the matched. Uh, you want the mag. You don't want the magnetic loop to be open and large. You want
right, right.
the wires going to and from the capacitor and the chip to be right next to each other or even twisted.
I see. Yeah. For what I had the switcher, I had a pretty tight layout, but I don't know. I'm pretty convinced that a switcher, maybe if you got one that was always, was only changing the duty cycle of a constant PWM, you might be able to filter that successfully. But this thing that runs in bursts, forget it. It's like it's like a rambunctious child banging around periodically, and you just can't anticipate. It's not cyclical in any kind of like way that's going to lend itself to filtration. It's just unless
Well,
maybe like you said, you had a
there's a
giant
special
capacitor.
there's a special switcher. It's either called constant on time or constant off time. When it gulps,
Uh
it always gulps at the same frequency, and then you use a one of those T filters, or I forget. There's a special filter that,
pi filter, the topology where you have inductor in series, capacitor to ground, inductor in series, capacitor to ground.
and then you block exactly the frequency that it always creates for you.
Yeah, yeah. Yeah. Well, these chips, I mean, they're not much. The
Well, that
inductors can get pricey.
yeah, that variable frequency thing, I think that's a known problem. Like one of the chips I use comes in two versions, a constant frequency one and an adaptive one.
Yes.
I guess the adaptive is probably more energy efficient, but they say that it can cause noise problems. So I mean,
Yeah,
yeah.
I mean, it'll cause audible noise even. Okay.
I would have thought that the 200 milliamps would be enough to make it run continuously, but I guess not.
Well, it was, I mean, it was like kind of almost continuous, but it was like fluctuating. And I mean, I could see like if I probed the ground on the board versus the P2 edge, there was an extra 100 millivolts of ground noise. And it was just like kind of periodic, but not exactly the same period. It just looked like random trash noise in chunks.
Yeah,
But
also maybe if this board was 4 layers, that could possibly help it.
yeah, yeah, that'd probably do. Yeah, because it's just two, tried to make it inexpensive. Oh, my laptop. Better get my power supply hooked up. Don't need one of those surprises. Let's see here. The screen dimming means something. Okay, back in business. Yeah, James, something could probably be designed to work right, but I don't know. I think this is going to work fine, but I just want to just get it proven, have something I can work with, and then do software development, and then ultimately make a board that has the P2 on it with all the switching power supplies that are properly isolated, and then have this circuit on it minus the 1.8 volt supply, and maybe spread out a little bit.
Yeah, just thinking like kind of a funny idea or so. Like if it's just a little bit away from continuous operation, then just adding a little resistor or so might be less thermal dissipation than a linear.
Yes. Oh, it would be. It would definitely run. It would definitely run cooler. Yeah, this thing's gonna run really hot now.
Yeah, but I mean, so what? You already have the main chip getting hot, and this you just have a regulator that's just as hot. I mean, it doesn't really matter.
Yeah, I know. It's just more of the same.
And the P2 board has plenty of power, so it's not really a concern.
Yeah. Yeah, it's not. It's okay. I was when I had it running, I was, now that we can do 1080p again, without needing one of those big bulky, converters, I was playing with that little 5 pixel wide font, which has like it's a 2-bit per pixel font, but the characters are only 5 bits wide. So there's like black and on, and then there's two intermediates, right? So black on, and then we get two intermediate levels, and those things visually dither so beautifully that you would never think that was only those characters were only 5 pixels wide. But the beauty of it is you could fit a lot of code on the screen at once, so I really want to kind of utilize that sort of thing. And it's kind of a minimalist approach, but it looks so good. I'd like to put all the tools ultimately on the chip so that um, I could have something that just always works. And then it would be fun to be able to, like I have some people I'd like to be able to show how this stuff works, but going through the PC route, and getting all this stuff configured, and then all the funny stuff that has to go on to get to where you can do anything. It's just, and it's so tenuous, and then it can easily break on them. And then we need something that's just like runs all by itself, lets you work from first principles, you know, up, and doesn't give you a hard time, and is perfectly repeatable. Are there only 5 of us today? 1, 2, 3, 4, 5. Let's see here.
Yeah, I
There's
didn't.
five of us here.
Are you talking just the power?
What about the power?
You were just describing the dream chip or the dream something.
Oh yeah. Well, I
What was
want to
the-
make I want to make a little P2 board where I put the tools on the board, like all the software tools, a couple of USB ports so that we can run like a thumb drive, and then a wireless mouse keyboard dongle, and just have like a little computer, that you can do stuff with, that is not at all reliant on any kind of other system. It's just this crazy thing I've had for years thinking about. I want to do it. Some people rightly point out, well, that's not how things work today because people need the internet on their console. And I understand that, but it is that like every day I encounter stuff on my PC. It's becoming just, maybe if I had Linux, I wouldn't feel this way, but Microsoft, they're now throwing up panes, like hogging up screen space of junk they want me to agree to. It's like, it's my computer. It's supposed to be my computer, not your computer.
You will still feel that in Linux too. Well, it depends, how much you clamp it down, but the default install they're getting not to feel like your machine anymore.
Yeah, yeah. You're just kind of relegated to like guest status, and they're gonna dish it out, and you're gonna take it.
So how much
I've got the same dream of the P2 being the computer, period. And the story.
Yeah, that's what I want to do.
You, Jim, for your genius to allow us to be able to do that.
Well, it can be done, it's unfortunately just a matter of software.
I've
But
made a huge lot of progress in the past month. Well, I was showing you some video display stuff, HDMI. I've just set that aside to work on the foundational bits. And I've been going crazy on the USB side of things. And through that, well, I keep all my code up in Fossil repositories. And on one of my trials here, I've had it starts up and it stores internally. It stores its data in a format that can synchronize with Fossil directly.
And you're handling the files on your side.
I'm writing it straight to the format that Fossil speaks.
Right. Okay. So you can interchange with them and their whole system.
I've got a ESP32 is just a serial pipeline. It opens the HTTPS, does the TLS around it, and gives me a serial pipe to my Fossil server. And Fossil was designed from the beginning to just work over this serial mode. It's got a little format that swaps chunks of serial data. And so I connect and Fossil clone, pull it down. Yeah, I'll set up one up there. I'll set up projects up there initially. And then Fossil clone to the P2 directly. And I've got, it looks like a Fossil sort of interface where I'm Fossil writing data to a table. And then I Fossil commit him the same syntax I'm used to and put a commit message with it. And it will shuffle the cards back and forth up to the server. And I can go pull that down on another P2 or on my desktop.
That's actually really getting some utilization of the cloud, right?
And I just use it there as a dumb swap, media swap.
It's kind of like it's an archiving facility is what it is, right?
Yeah. So I never lose, never slip. All the work I do on the P2 is captured there, and I can pull it down in another one and keep working. And I've got another just a command to get and post, so I can get a web page. And I've put this little bit of code on the ESP32 that does the nonsense and gets this giant web page out there now, strips it all away, and gives me a markdown format text. So that's what I get markdown on my P2 and work with that.
Wow.
I've done just very little bit with that, just to see that it could be done, but all on the USB driver. That's what's moved a lot of this now. I can put
So when you say USB driver, do you mean you're using the built-in smart pin facilities for doing the USB signaling, or you're using like a virtual COM port to get out?
I'm using the smart pin signaling.
Oh, cool. Okay. Yeah,
And I can plug in, I use the same serial host, the P2 2-port USB connector, and I can plug a hub into both of those, and I can get 16 ports.
Oh, wow.
Plug in like an SSD. I had a 1 terabyte SSD plugged in, or a 128 megabyte SD card with a little USB reader. I had started, and I see Steven stepped away, but I had started using that dual file system for the flash and
yeah. SD.
SSD, or the SD card. But since I moved to the USB, I'm just kind of I'm not going to use the SD card. It's just
Well, yeah,
a more
isn't it
robust.
such that, yeah, the little thumb drives are the way to go. Those little SD cards are fine for cameras or something where you want to have like, built-in super hideable storage.
Yeah,
But for
yeah.
stuff that you want to move files with, it's actually better just to have a thumb drive because it's,
They're a little finicky. Yeah. Once I took up all the code space for the USB driver, well, there's still a block storage layer there, and I put the file system on. I say I have a lot of automatic assistants out there doing this.
like Steven.
That pulls in the FAT32 file system driver that you and he worked on, and all the little wear leveling and stuff like that. Took the bits, massaged it, and put it on top of the USB block storage interface, and added an EX-FAT to get to the giant disk sizes. And now I still want to write the flash, but I only just do settings there, and I've got a little append-only that kind of does its own wear leveling. I'm only doing little bits, and it just kind of writes continually off to the end, and that's just settings for that part. And last night I stuck in a USB audio. Oh, I can't unplug it. It's in the middle of something, but there's a USB little audio chip, sort of like it's got the analog, or it's got audio in and out. I stuck one of that on the USB driver. Now that's isochronous. The timing is critical, but the block size isn't.
Yeah. So you have to be on every millisecond. You send a packet with
Yeah.
enough samples to fill that time frame.
And that is interleaving with, I'm moving large files between devices and running audio at the same time. The audio keeps steady. The file storage will dial itself back a little bit as it needs to keep the audio flowing. And the keyboard, mouse, and stuff is still, that's just noise. It doesn't take any time, really.
It's like a
But
switcher.
you need to have it sampled all at the right time so you can catch, peek at the keyboard and stuff, and not miss those either.
Neat.
So that's made it really flexible. I hook up to a lot of external equipment. And with serial ports. So I don't know, but just the $5 USB to TTL or the USB to RS-232. A variety of companies out there make that, and I didn't realize that they all need their own version, their own adaptation.
The driver?
Yeah. So
Yeah.
I've got 3 of those covered, variations on 3 of those covered now. Plug in things like, it's also in the snarl of wires right down. I can't lift anything up without everything lifting. But that has, again, with the helpers, once you had the first one down, the rest were easy variations. So anyway, you can plug it in, it'll auto detect what you plugged in and makes a map of everything out on the USB hubs.
Now, you're using Lisp to do all this, right?
Right now, I'm all in spin.
Okay, so are you using structures? Because I realized when we started writing the USB code, this is why we need structures, just to handle something like USB where there's so many little pieces of data that you have to keep track of that are all uniquely
I
named
had
and
been using structs when I was in charge. It's harder there's not so many samples out there, I guess. I have to be very explicit if I want structs used. But yeah, no, they were fantastic, and that's just what's necessary for this, or useful for this, to simplify it for our heads.
but you're not using them though, right?
I haven't. Yeah, right now, frankly, I don't know what's in there. It's going so fast, and it's delivering what I need, and making no promises. But I did post. There's a link if anybody wants to follow along. All the USB stuff that's happening. I love the smart pins and what it can do, and it was playing with the PDM mics, and they blend well with the ADC stuff in a way that simplifies some drivers. I was playing with speech to text. But then this USB audio went in so fast. I'm just exercising it, and I might not go back to the I don't know if I'll put the PDM mic in or not.
Okay.
Right now, it's a loopback. I've got on that one USB adapter, I've got the audio out and plugged right back in, loop back into the audio in, into the microphone. Have all the levels dialed down on the audio out, so it's not crushing the mic input. And it's churning through, making a giant DSP library.
Oh, so so when you're saying text to speech, I mean, or you said speech to text. Okay, that's like a whole science. So you're having Claude somehow build this.
It's on the same. It's well, what makes this possible? Step back to last week. No, step back to the USB, the USB driver again, and its serial connections to all my devices. And lots of these devices will have this little dance it wants. We'll type this in, set this mode, wait for this to come back, look at that, send another, make a decision, send another, chunk, dance, okay. And now sample, nor drive up, drive down, whatever. I don't know, Tickle, Expect is an old library that is made just for that. And I left it in the USB driver for anybody using the serial port drivers. There's an expect language that you can specify without recompiling and rebuilding any spin, you can specify in a config file what you want to feed, what's the dance you have to do for this device.
Okay.
And that gave me the flexibility now. Yeah, I want to use it like a computer, not recompile my whole computer every time I want to add something. So
Right.
I had to lift it up, and that's why I'm using Lisp, is to lift it up a level that I can now read my code in from storage and execute it. And that's on Exploit. So I've got that expect communicating with these devices. And I've got a language around setting up pins where I've got a pretty simple language to set up a pin. There's a pin, it's this type. Now, here's a variable, it's this type. I bind it to a pin.
Oh, cool.
And then that's a fact.
Hey, that's interesting.
This fact and rule thing from the old expert systems.
Yep.
I stack up these facts. Here are these variable pins. There's an intention behind why I've set that.
Yes.
And there's a range to it that's a legal valid range for this variable and the unit type. And you start attaching that to these variables, then you can reason about it.
Yeah, that's a great idea.
The inference system can go through and say, you've done something wrong. You can't multiply this by that. You can't control this, or that relay shouldn't be open now because you're driving it for 2 inputs. All of that stuff I wanted to get to, so I had to create this language.
That's pretty cool. There's so many ideas that could have popped up at any time, but like have eluded me or whatever. But this matter of like a pin having a variable or a couple of variables assigned to it, you could actually take every smart pin function and build some kind of translation through some variable states and whatnot. And then maybe it would take a cog or at least a library that you call that would configure the pin.
Yeah.
But you could then take everything, like what does the customer want? You want PWM? Then just set this mode variable and then read and write these variables to control the duty and the period. And you could like simplify the heck out of so many things like that.
And change, you can, in the middle of what you're doing, you can check the voltage on there. Is this floating or is there something even attached? Okay, it's attached. Now you start to, well, what's it attached to? If I put a pull-up on there, how is it responding? And you can look at it from the adjacent pin.
Yes.
And be sensing from the adjacent pin and do a whole research around what's hooked to my pin right now and what mode do I need to be in, and to do that all in a configurable way that you can script from the outside and not recompile it every time to do those things.
Yes.
Chip, I'm sorry, I got a dumb question. Just before his last statement, when you were talking about, I'll just say, kind of like creating a language and assigning things, can you do that with a lookup table?
Yeah. Well, yeah, you could have some kind of thing where, depending on, let's say you want to map all the smart pin modes to some variables. So you'd have to have some sort of control variable or some mode variable that sets like what kind of configuration do you want? And then you have a few variables that affect after the fact. It's just kind of like read pin or like write WR pin, WX pin, WI pin, but with a little helper stuff in there to make it simpler so that the customer doesn't have to worry about all the bit fields and everything. he just says at kind of a high level, I want a PWM doing this at this time. And then, I mean, we could just make that as a callable library that just like sets the PWM, and takes care of all the little persnickety
So,
stuff.
so that's what I do with the language. I can do that live. I've set this and bound it up, and I can say, now set the value on it. Boop. And it comes out to a relatively small vocabulary
Yeah, I bet
that
it does.
I used to train an LLM. A tiny LLM that I'm running on the P2.
Whoa,
So I can type English, and it
man.
converts it to the language, my subset language for configuring these pins. And then I added the layer. That's where I got to the speech to text. And both of the LLM and the speech to text is a neural net training process. And there's a lot of similarities between the two.
So so you made a large language model but it's not exactly large language, but it's a concept,
Yeah.
something simple that is resident on the P2 that then takes your queries that are kind of like can be really ham-handed and simple if need be, and it translates that into like configuration and settings on smart pins.
And I can ask, what is this set as, and what's going on here? And in the language, if you do this facts and rules thing, and you can do the forward chaining inference through it, and that's old school. And I can ask, my pin is low, my relay isn't on. I can ask, why is my relay not on? And it can walk through all the rules and say, well, either this or this has to happen because this has already happened, so that's not why it's off. But you also, in this whole chain of logic, need to have this and this also.
Gotcha.
So you can debug and troubleshoot. I'm trying to get just spoken language to my bench test unit, but at the moment, I can just English it and ask these questions, even though my language was so simple. Just throwing that bonus on there that we can ask it things out of order. Every 3 seconds, toggle this pin, or toggle the pin at 1/3 hertz, or things like that. Translates into the small language I've got.
That kind of turns the P2 then into like a function generator that you can just have a conversation with.
Yeah.
And then if you want to do, was the idea that with speech to text, you could actually talk to it and say that? Can you make a 1/3 hertz square wave on pin 25?
Yes, exactly. Or I could have my head down in probing something, and I can say,
exactly.
what's the voltage on this pin? And well, it would type out. I don't have the audio out yet, but there's no reason. That's the simplest thing after it all.
That's crazy.
I can have it tell me the voltage on this pin, or
I've
set up these 8 pins. Configure a phase array something or other on it.
Yeah.
And have it do that configuration. The DSP library is churning on that right now to do that phased array stuff.
That's wild. I wouldn't even, all these ideas are possible. I don't even know how to push that envelope because I don't even like think that way, but that's pretty neat that stuff can be built with the aid of this AI. Because it's not something like you wouldn't attempt to make an LLM, right? That's like not your wheelhouse.
Right.
But yeah,
and I was down the road. I thought I might think about it, but it was actually a prompt in the forum last week. somebody posted they had ported an LLM. They've got little ones. They're running on ESPs and stuff like that. And
Whoa.
the token rate, the generation rate, well, and to be fair, that was just a simple port to a single cog, single processor. And I said, well, I've got 8 processors here. Let's make the most of it. And I told Claude, here, do something like that. Use the whole P2 to its optimal, and it's got some pre-processors, post-processing. It's got 3 workers that grind through the math and keep the pipeline full.
Wow. That's cool. Man, that's like, I never
And
even thought about this kind of thing.
it took about 6 hours to do that. It went
Wow.
out and did it. Well, it said, because I've got that limited vocabulary.
Right.
Well, actually, that was a speech to text, but even in the LLM itself, I'm not trying to capture every word in the universe.
Right.
I think it captured about 200 words
That's crazy.
that
So
you
it can
can
actually,
use, and
but that's useful for
yeah,
making test equipment and and like diagnostic stuff for bench work.
in
You
your
don't need a
limited
big
realm, yeah,
vocabulary.
yeah,
Yeah, I've often thought that it'd be so cool to have like just a voltmeter that could tell you the voltage.
uh-huh,
Because have you ever tried to, like, it's hard enough to get the probes in place. Then you got to
exactly,
look off and see some stinking
exactly, yeah,
low contrast LCD that's not at the right angle.
yeah. Dusty still. I sharpen my probe so I can poke it into the metal and it won't wiggle when I.
Right. Hey, hold on. I'm going to be back. My mom's calling me. She needs something. I'll be back in like 1 minute. You guys talk amongst yourselves.
Okay.
Hey, Shannon, can you hear me? Shannon? Shannon, can you hear me?
Yeah, I gotcha.
Okay, what you're doing just reminded me of Admiral Grace Hopper. She's the person who created the first compiler way
Yeah.
back in the 50s. She designed COBOL language. And she was an admiral for ages. But she's the person and her team who first made computers be able to speak English like we talk to it now,
Right.
versus flip data switches. I worked on the old 1130s and stuff like that. So yeah, that's what you just reminded me of what you're doing there. Real fascinating. That's why I asked that question.
So I worked on a lot of this stuff through last fall and through the spring, trying to compact as much of this all on one P2. And I came up with a lot of clever arrangements that sort of made it work, but it was slow, and the development effort was really slow, and I've kind of backed up and just, let's go the other way. Let's get full functionality here, and we'll pare it down after and see what fits. The architecture is just, I'm going to have slots on my board for several P2 edges, because the whole speech to text is taking a whole module. The LLM takes a whole module, but I'm making a point to have serial communication between these modules, so they don't have to look into memory buffers and stuff like that, but have a way to shuffle this data around. And
I take it this is all in assembly language, yes?
It's in PASM where it needs to be for speed, but I don't drive it down there initially. I'll stay in spin if it's comfortable and not time sensitive.
Finally learning after all these years, assembly language between Steve Morocco and another guy, I can't think of his name, who both have been, well, Steve went through all the P2 stuff and codified everything, and some we wrote some very extensive books on it, which I'm reading. And then another guy who actually I can't think of his name right now, he started P2 assembly for beginners, and it's all very logical. And unfortunately, I got to take this call. Sorry about that.
Yeah, I read that assembly book too, and learned a lot of stuff that was fuzzy that I used to just do because that's what it was done. But now I understand it better. What's anybody else cooking?
Sorry about that. That was the VA. So yeah, so it's so the assembly language stuff is coming a lot easier. So that's why I asked how much of your stuff is in assembly.
Yeah, seems like half, just ballparking it. I'm not paying that close attention.
It's curious.
And the USB driver stuff, I've shared in the forum link that anybody can follow along and pull down and try it out if they want. Made up some docs to show some example code and how to use it, put it into a project.
It's pure magic, I take it.
Terry's April Fool's joke. I missed that call. What was that?
Let's see. When was that? I have to go look and see. Yeah, that was from 2024.
Talking to your Christmas lights?
Yeah. Well, someone had actually done a what they called a GPT-2 small model in an Excel spreadsheet, and I'm like, hey, it's close to April 1st. I'll just plop this out there.
Fun. I'll pull up the forum link for.
I was curious. So is it some type of like transformer model, or is it like a tensor, or what do you got going on with how you're doing that?
Yes, I saw all of those words scroll by while Claude was making it.
Outstanding.
Seriously, I did not touch the code one iota. And it delivered a functional test, executed it, and I can use it.
That is amazing. I only got in on the end of this conversation. That is awesome though. I mean, I had Claude work me up a working vector display with debug output asteroids. Never touched any of the code. Never touched any of the code, and it did it.
Some of the HDMI stuff I was showing. Well, I didn't show much of last time, but I'm sending an SVG, well, S expressions, but effectively vector graphics, vector commands in a stream, and having the video driver read that and figure out line by line what needs to be on a pixel, and it does three lines at a time, and it's racing ahead of the display as it gets pumped out to the display.
So You take a
Yeah,
vector input and turn it into a pixel display kind of thing.
yeah, yeah.
Nice.
And because I did all this on the Edge with no PSRAM on it. Yeah, so I was just getting clever, and I was pushing pushing Claude as far. It's stunning. Just think about it, and a few hours later, it's there. Um, the So that came out pretty nice, and it comes out better with PSRAM. There's more space to play with different things, but right now, I mean, we were talking about, and Chip was talking about in the beginning, just console straight up text and do your work on that. But I might press this vector display enough and see if I can get a user interface along the lines of BOS.
Oh yeah.
That was my daily driver for 8 years.
Oh man, I wanted a
And,
B-Box so bad.
uh-huh. And the peak port, the is what I'm calling now. My DB37 is the physical connector that the B-Box Geek port was.
Oh, okay.
And by default, I'm having these pins automatically set to the Geek port setting. Some were analog, some were digital, and well, here's some more fun you can have with Claude. And it didn't do this last year. I tried a bunch, but in both KiCad and Libre PCB, I just opened some empty projects just to get the file format there. And I pointed Claude at both of those folders and said to create a schematic, capture a schematic. Don't do the layout, I'll do the layout, but I want the connections, all the nets connected that were discernible from, that are obvious. From the P2 Edge connector to the DB37 with a pinout like the Geek port, the BOS Geek port, and power that board with an ATX power supply. So it's easy to get my negative 12 volts for the Geek port. And ka-chunk, it produced both of those projects that open up and are nets connected. Schematic is laid out plausibly, not jammed together.
Nice.
And I said, and make the circuit board footprint 96 millimeters wide. And just left it at that because I'm going to place the parts. And Libre PCB actually came out a little bit better. I was surprised than the KiCad. But anyway, I'm lots of the finicky stuff that I hated doing was finding parts, finding part numbers, finding data sheets. All done, is all linked into the project, and it went too far. Actually, I wanted to use the P2's native ADC and DAC. It went out and found the BOS, the B-Box schematic, or what the circuits that fed the Geek board anyway, and went and pulled all those parts and put in the ADCs and DACs.
Nice.
In the schematic already. I said, oh, that was great, but back it out. I didn't want those in there, and chunk. They're all backed out. So, yeah, things are moving a whole lot faster in the past. I mean, this was only available easy to me 3 months ago, and it's just it's so fast.
Yeah, I think about 9 months ago, I had Claude do some schematic updates for a project I was working on, where it's like, hey, I just need you to duplicate these blocks over and over and over again, you know, and it, you know, and renumber it, and you know, all of that kind of stuff, and it did not do it great. I bet it would probably do a whole lot better now, because the things that have happened in the past 3 months are pretty amazing.
They are, yeah.
Yeah, I see it just getting better and better all the time.
Yeah, so things are going. Yeah, I need to get it on a circuit board and get the jumble of wires out of my bench. Now things are getting nailed down. Real-time clocks, I want that for the file system, and everything else. That's got to be in there. And then the serial connection, I want several of them, to adjacent edge-connected boards, where I'll have one primary, but through the serial do the, well, I can put the audio into the speech to text one, which will communicate to the LLM one, communicate to the main board, and the design rule checker in the PLC, the machine control, the bench tool, that'll be the final word. No, you can't do that. It's not legit. It won't go. I'll have to now give it like a compiler. It gives back why didn't it work, and it'll give back English, well, encoded words, but that could go back into the LLM that could refabricate it and send it down again.
Hey, Shannon, this LLM thing that it creates, now the LLM, the program's probably not very big, right? Because it's all data driven.
Meaning data not very big, as in how much code is on the...
Well, I guess I could ask you, how much code is it? Because the LLM concept is really not so much code as it is process, right? So there's a lot of data that some small kernel sifting through over and over in order to come up with outputs.
Yeah.
So that
it's, well, I wanted it, I said, take everything you need here. I need a console connection, so I REPL, so I can see what's happening and command you to do things. But it maybe had a cog left over, because some of the stuff is pipeline and some of it is just grind through in parallel.
And it probably did all this in spin too, right? Or did it use PASM?
It did. It does PASM when it needs to, and very well. It'll start and spin. I've pushed a few things down in this USB driver. Well, this is kind of slow. Well, why is it slow? Well, we're still up here duplicating something in spin. So push that down to PASM, and I got a 40 time speed up for that particular file system thing. So
interesting.
And it toggles in and out of, well, I've understood a lot more about XByte and where it applies and where it doesn't. Some things it'll speed up great. Some things need the flexibility to be interpreted, and there are some things that are just, well, there's only 12 operations, and there's no benefit to having the the rest of the machinery around it. So it helps me make those decisions now, and it's pulled some stuff out that I used to have an exabyte, which was fast and snappy and stuff. But we can go faster and do it in PASM.
Now, were you using Stephen's exbyte explanation from his P2 knowledge base?
I point.
'Cause how did Claude get so aware of exbyte?
I did when that new sheet came out. I did point them at that, which is all the data that's out there on exbyte is all in there. Took me a long time to find. Okay, yeah, that's all the references. They're all in there. And I was surprised to see what I had produced ended up in there, which is great. I produced the minimal subset to get these AI to recognize, to be able to do it.
Okay, so some of it was kind of your training.
Some of it was, but I used to go to the knowledge base MCP that the AIs use, and Stephen's got great documentation on how to set that up, and I did that one time, but I don't anymore. Usually the first prompt I do, I load up an agent in a folder, and I give it the URL to that MCP, and I say, make sure you load that up, and it goes out there. It reads the instructions, populates what it needs to do, and uses it. And I don't configure stuff anymore. And frankly, I don't code stuff anymore. I watch stuff go by. I learn architecturally what works and what doesn't work from this. And I make sure I stop it pretty regular and say, generate a good getting started document for me on this language that I've been working on. I say, make some user documentation for this. Getting started, how do you get in there? But mostly because it's a foreign way to think for people who want to just tell it, do this, now do this, now do this, now do this. This is load up, back, and the relationship, and then they just say behave, and it'll do that. So, I had Claude write up useful sidebar stuff on why do we think this way? Why are we doing it this way as opposed to that way? Now let's and just broke it down into, which was useful for me. I've been developing it, telling it how to do this, why we wanted it this way, but it's produced stuff and rehashed it in a way that made it useful for me. And as new things get added, I get that updated, and then I go in and follow yeah, okay, that's what's happening. Yep, that works good. Oh, no, that's not behaving. That's not behaving yet. Bug. Tell them that's not behaving, and get it fixed. And oh, that's not behaving. That's not quite right. Fix it. That's not quite right. Fix it. And I'll see. I've gotten it mostly, and you'll see in that repo that's up there on the USB. There's a bunch of kind of rules. Code smells, Claude smells, where it's learned from the corpus of bad code on the internet, where, oh, we'll just wait. We'll just, 3 seconds wasn't enough. 4 seconds seems to work. We'll go with that. No, I don't allow that. And I'll force it to iterate. You're waiting on something. Is it something you can see? We'll pull it and see, and go on that. Don't just give it enough margin. If you see margin roll through or settle, or those are all keywords that they're doing it wrong. and I'll force it to iterate through, sweep through everything, find out what it's looking for, and justify it. Or it's in the spec. It's in the spec. I have to wait 50 milliseconds. That's just it. Okay, good. Document it. There's no magic numbers, and all the numbers that are in there are all supported. Whether it was, there are some that came down to, yeah, no, we swept through everything. This can't be found. And there's might be an interesting bit on one that we couldn't pin down. We were trying internal pin checking of the in state on an adjacent pin to try to understand internally what inside the smart pin needed to switch in time, and it was missing. And maybe you'd want to dig into that, but it came down to a magic number that has been in the USB drivers forever, and I was trying to drive it out, trying to figure out what it was. And in fact, that number can't be driven out. But if you drive the clock too high, your whole system clock too high, you'll expose another issue. So we did isolate and found a way to set that magic number based on the clock speed of the whole processor. So I'm not writing syntax anymore, but I'm spending hours working through these processes with back and forth with the model until it can prove to me through a test that has produced something tangible that a thing is the way it is.
I see. Yeah, that's a totally different way of thinking.
It's
See, the guys that are good at this and they're getting something out of it, they're figuring out how to work with it like this. And it's like unorthodox for programming. It employs programming truths, but from like 30,000 feet.
But you can still recognize wrong.
Yeah.
And architecturally broken things. And anyway, being very strict on some of these things and watching what's going on and looking at the summary of what just happened. It'll grind about 15 minutes on something, and if it's fixed, it's all fixed and committed, and here's the summary. Or it's we don't really understand it yet, but here's what's going on, and we're going to explore this next, and we're going to try that next, because this will weed off that branch of the discovery, and that'll weed off that.
It sounds like you have it iteratively trying code and looking at the results and then turning on that all on its own, so you're out of the loop for the most part.
Yeah, I come back. Well, I've got 3 of these going at one time.
And so they're compiling, downloading, running, getting debug data back.
Yeah.
Okay, so it's really...
I've got 1, 2, 3, 4 edges going all the time. 2 of them were hooked together with CAN bus for a while, but anyway, so I have to sometimes, hold on, don't do that yet, because I've got another one running on that edge right now. And using the prop plug identifiers, that's Peanut TS uses those identifiers. So it's easy for me to specify, you work on this one, you work on this one. It can go on the USB and find, okay, now I'm going to hit that one and that one. And it doesn't matter if the dev USB whatever switches around on me, the COM port.
Wow.
That's been huge.
Neat. So you actually have it doing the iterative work to prove things out and move forward.
And it comes up with all that. I don't have to explain that much. It generally comes up with its own research plan and iterates and tries and weeds, prunes off hypotheses that fail, and comes down to, we're down to 3 things. We can test this and discover if that is, and I don't have anything to test for this, and it'll go back, what are you suggesting? And I'll be in the middle of it sometimes and say, oh, wait, now, remember, Spin 2 has tasks. That's what you need to do here to stagger these correctly. You know, and I'll chime in like that. Or Cortex got something for this, and it'll take my input, and sometimes I just pull something out. Oh wait, that's starting to sound like such and so, and it'll go out on the internet and start. Oh yeah, no, I see the parallels. I see what you're thinking about, and to pull that back in and iterate on it.
Wow. Francis, are you following? Can you imagine doing this kind of thing?
Yeah, it's pretty cool stuff. So it's essentially having some assistance that, you know, you give them a little guidance and input, and you're mentoring, you know, essentially, or whatever, and directing how they're doing stuff, and then off they go. So you've got a team. You're
Yes.
the architect and the head of the team, but then you tell these minions to go out there and do this fun stuff, and some of them go off in the weeds, but then you drag them back in where they belong, and
Yep.
sounds cool.
Yeah. I think it's hard for me. I've always hated management. You know, I don't really do management. I just try to manage myself. But my brother does management. But anyway, maybe my management is I'm so impaired management wise that I can't get, like, I want to be doing this stuff too, but I don't know that I'd like to be doing it. I think I would. I think it'd probably set me free and allow me to like do a lot more. Like Steven says, it's like he has a big exoskeleton on. You know, he can handle all kinds of big tasks. So, and that would be fun. I just got to like figure out how to do it.
So I don't like the management bit either, but I do like talking tech with a bunch of nerds, and that's what it feels like. But I'll start with, let's come up with a plan. I'm thinking about this, and we'll be back and forth maybe 8 hours coming up with, here's what we're trying to build, here's where we're going, what's a good way to do it, go research this, give me a little summary, research this, give me a little summary. And I'll sometimes swap and say, what do you think of that model? What do you think of that one? And let's blend them together. And oh, there's a new idea. And then, and here's the key part that makes everything else churn good and keep on track. They'll go off in the weeds. And they love to run away on tangents if they're not guided. But how I guide them is, well, on that link, go to my fossil repository. Is the first line in that forum post. There's tickets. And I say, here's the whole plan, give you a good big document. Right, that's the grand plan. Now, parcel it out into tickets. Work items that have to happen in what order. I make them name them with a preceding number that gives them some sort of order and clustering. And they'll do that up front. Well, their head's clear and the plan is there. Get all this laid out, all these tickets laid out, so we can never stray off. We can come back, we can do something, but always know to come back and say, oh no, start picking up the 700 tickets. Start working on those. Or wait, this one's still open. This one's got a bug. It's hung up until this other ticket gets cleared. And it'll make those dependencies and make notes in the tickets in the repository for the next agent. When I wake up the next day or my machine reboots, I'll say, agent, go to this repository. The whole plan is laid out there with all my notes about no magic numbers and stuff like that. It's all in there, and it looks through the repository and says, oh, I see what's going on here. Let's pick up a ticket. Okay, let's start chunk. getting it in the tickets in the repository, they kind of have their own little way of, oh, I'm writing a memory, I'm writing another file and updating, and those just get out of sync way too fast and diverge from what you're trying to do. But having it in a ticket system keeps everybody on the straight and narrow, and you get things done.
Now, would that be a skill? Is like handling, you know,
they say, and I spent a little while, oh yeah, skills, what's the thing I need to know? And at first I said, well, okay, smarty pants, you know how to make a skill. I don't. Make yourself a skill. Figure out fossil, make yourself a skill, and boop, and there it was. So now they know how to deal with fossil, but it's not too hard. I don't think you need that. Any AI can look at a fossil repository and understand it.
Yeah, this is like mind expanding. My brain's too brittle.
It's my problem. Well, until last week, I was constraining myself on what I thought they could do.
Yeah. I underestimating.
And I wasn't asking big enough ask.
Yes. Yeah. Underestimation is the problem with user underestimation is the problem with AI.
Yeah, I couldn't.
It's not.
Well, I used to only ask it to do stuff that I knew how to do myself. Shannon, and maybe that was good for the first couple of years, and I was working with this and developing a rapport and understanding what their weaknesses were and stuff. But now that I'm confident, I know what's going to come out. I let her fly, but also ask. You have to have a tangible artifact that proves this happened through hardware.
Right. Yeah.
Because they'll happily pseudo solve this in the back door, and here's your test result, and it's not real.
Yeah.
Hey, Chip.
One time I was. Oh yeah, Martin.
Sorry, hey Chip. It sounds like you didn't get your brain back after Stephen Morocco ripped our brains apart 2 meetings ago. Remember that?
Right. Yep. Yeah, well, it is kind of, it's a different way of thinking. You have to give yourself license to allow yourself to think these ways, and then to not underestimation is user underestimation is the limiter with AI. It's not AI.
Yeah.
I forgot what I was gonna ask. I had some question.
The next thing I have to ask about is, okay, well, all that other stuff I don't like doing, like building a business and marketing material and stuff. I hear they're good at that. I don't even know how to ask it to do that. But I like to say, make it go.
Yeah. You know, it's funny that AI, it seems to still need humans to steer it and give it impetus, you know, to do anything, and it's happy to comply. But I wonder if like it will be a soon thing that AI starts designing and building its own products for its own reasons, for its own goals.
Then you need to watch the movie Terminator. That's where things get a little out of hand.
Oh, right.
That's scary.
Well, right. I'm racing as fast as I can to make the most and make my own piece of hardware here that I fully understand. There's no operating system beneath me. My application is on the hardware where it should be, and yeah, your dream to not need a host and do work on these. There's so much horsepower in these. I mean, the original B box didn't have as much horsepower as this.
Wow.
Had slightly, well, not with the PS RAM. That had 4 times the memory of the first machine I wrote B on for years. 8 megabytes I ran for years on B, and it was the snappiest thing in the world.
Yeah.
it still is snappy compared to the burdensome operating systems now.
Oh, I know.
How much are you paying for this Claude to do this? I assume this is more than the free version, right?
You can do an awful lot with $20 a month. As it became more valuable to me, I stepped up to the $100 a month, and that's kind of where where I want to be normally. Use that much, but just in the past 2 months, it has been churning out so much so fast that I was just, lost opportunity for me. I guess so I pay $200 a month just for a couple months, and I'll probably dial that back down. But this Fable model, Fable 5, I don't know if you've heard of it, or Mythos, that just came out a few months ago, is really genuinely head and shoulders above everything else, anything else for P2 code. I keep other services going. I keep Perplexity at $20 a month, and I've used GPT a little bit, and I use the models through Perplexity because I get to try models from different places, and $20 a month on Grok, and Fable is far and away the best for Propeller coding.
And now, see, the thing is,
Grok is the fastest one by far. I use Grok to do that Arduino ESP32 web interface. It'll churn that out in 2 minutes.
yeah. Well, the thing about Fable being the best for P2, the thing is, it doesn't have any special P2 training. It's just better at reasoning and assimilating like knowledge-based material, these MCPs, and utilizing them, right?
Yeah, except I mentioned last time, I think, it still will pop up just about every project. Oh, I've hit a few things. I'm just going to make a little note for myself. Greater than equals. And this rolling off negative, the repeat something for n-1, it always thinks it's going to the array size -1, not n-1, n-1, it seems to roll off the bottom. There's something in the syntax there that it ends up, oh, I've stepped off the bottom of my loop. It didn't go up. It went off the bottom of the loop. Again and again, that's catching these models. And it writes itself a little note, and I noticed that. But
so it has like a strong predilection to think of loops in a certain way, and it can't be disabused of that.
Yeah, and without the parentheses around to make it think otherwise or something. Yeah.
I see.
I mean, even with the MCP, I think though that is in there, proper syntax, but it's just, overpowered by the rest of the world does it differently.
Yeah. Man, I wonder, putting an LLM on the P2 with you said it had about a 200-word vocabulary. And then it knows all the different things that kind of knows the gist of everything that might happen with those 200 words, right?
Right.
And I wonder, do you remember, I bet you that the code that executes that is not very big, but there's got to be a lot of data. There has to be like what amounts to a bunch of data to give it the personality, right?
The weights. It trains a model and sets all the weights between all these parameters.
So what you see is, you see a bunch of code then. It's making like data statements, or basically it's like making tables of like longs or words or to build all this stuff in. Do you see that in the source that it outputs? Or does it output a binary with a bunch of weights?
Honestly, I haven't looked.
Yeah,
These past two things, I haven't even looked. It delivers functionality on the desk that I want.
right.
With a bunch of tests around, I'd like to go back and study it because there is a little bit of optimization I think I want to do still on that. But or maybe I can combine these two if they're not doing the same. If they're not doing both the same things at the same time, I might swap
Yeah,
this. I'll listen to you and turn that into text, and then I'll feed that text in, shift out my model, and now LLM it. Do
yeah.
that on one processor. And I want to study it a little bit, but effectively, I'm going to say, Claude, can we do this? Do this for me, and it'll do that switch.
So this is using statistics, probability theory, and all that kind of stuff. When you were talking about,
It's
go ahead.
neural nets effectively come out as a big statistical engine. Yeah.
Yeah, it's like a bunch of multiply accumulates, right?
The and that's what's doing the speech and languagey bits. When it hits my language and my set this pin, this fact, this rule, that is old school logical symbol manipulation, straight up logical inference. And forward chaining and backward chaining is I have a bunch of inputs. This is good for a PLC sort of thing. I have a bunch of inputs. Walk through all the decisions to get to an output. Where will I end up with these inputs? There's backward chaining is I have this output. When we ask why did that happen, I have this output, and it walks back through all these conditionals to say, well, it's because of this. And that is not statistical math, probabilistic. That's cold, hard Boolean logic all the way through. So that's the nice thing to have this provable, traceable. That doesn't get out of whack, slightly misadjusted if it gets trained differently. That's what I like to have. The final word controlling the servo or relay or something that's driving my heaters and boilers and stuff. I won't trust that to the whims of the training set.
We used and working for Doug, he wanted to tap into like a vehicle CAN bus, because there's all these subsystems in a car that are, and by the CAN bus is so cool how it arbitrates.
It really is, yeah.
We should talk about that sometime. It just it's like a 5-minute thing, but it's like, how does it never waste bandwidth but resolve conflicts?
How does that priority is a physics arbitration. It's not we're going to agree to something. It's physics.
Yeah, no, there's nobody's stepping on anybody's toes.
Yeah.
It's a smooth thing, and everybody just follows the conversation and then see who wins, or who's still in agreement as they try to get their message across. And if you're out of agreement, go back, finish watching what's happening, then try again later.
So for this, I ended up arriving at these two sort of cadences for reporting a result, and a producer and a consumer, I guess. Back all last fall and the spring, I was making these elegant pipelines of ownership, buffer, pointer handling. So I didn't copy anything anywhere. And data would shuffle through just by moving pointers around. And you own it now, you own it now, you own it now. And that was great for a pipeline pushed through system. but I was getting to, as I started to hook it up to this machine control, that half of the stuff is not pushed all the way through, but is kind of there. I have a state, and then when whoever wants to look at it can kind of subscribe and say, oh, I'm interested in what that one says, and move this system through that way. And then I saw CAN bus. I said, well, there's the digital physical implementation of the more optimal data through the system.
Yeah.
And my son bought an MG, a 1980 MGB, and they have always had faulty wiring, and I end up cutting out the wiring harness, so it's up to me to replace all the wiring in it.
Oh, gee.
So I'm putting a CAN bus in a 1980 MGB with the head up front doing the headlights, and the one in the back doing the tail lights, and a couple behind the dashboard taking all the switch control inputs and all the indicator light and meter outputs on CAN bus.
You're talking about the Lucas. You're talking about the Lucas drive-by daylight only electrical system. Don't go there.
Yeah, don't wiggle the wire. The smoke comes out. The magic smoke. So I don't feel bad replacing that. But as I'm talking about my peak port, my 32-pin single module, I want to have multiples of these in the bench unit. But they'll use CAN bus on the background and merge the model of all of them together.
You know that CAN bus to just receive, right now we're just listening for messages. We want to see a complete acknowledged message, make sure it all balances. Then we just want to get that. And anyway, it turns out that just if that's all you want to do, you don't really need a CAN controller chip. You just need the CAN interface chip to make your own life simple. Yeah, and it's just an RX and TX signal, and then attaches to the line level CAN H and CAN L, and so they're basically just, you know, whatever you output will come back in if there's no conflict on the line, but there's never an electrical conflict because it's resistors that pull the lines back together. It's such a cool idea. But anyway, we captured all this data and we're trying to find like a certain type of data. Like we wanted to know the steering data. Okay. And we just gathered all this stuff into a comma separated value file, gave it to like what's it called? Claude. And this is an underutilization of the whole thing, but we said, okay, we move the steering wheel this way and then this way and then this way. And so it combed through all that data and discovered the IDs. It discovered that there were actually two different IDs that contained the steering data. One was because there's this high performance active suspension system that sends it every 10 milliseconds. But the default without active suspension is it sends it every 100 milliseconds. But anyway, we were able to like get those IDs. Now we can just strip off and know where the steering wheel's at all times.
Right. And just by listening for those. And that's what the controller, I mean, I went through and had Claude write the controller replacement so I could talk to just the transceiver. But two things. Well, one, I only cared about old classic CAN anyway. The two new CANs, the fast and there's an XL. You need license.
FD or something.
F and an XL. You need a license. And if you buy the chip, you bought the license to use it. And I wasn't considering going that fast anyway. But also what the controller does is you can just tell it to watch for these. I'm looking for these two messages.
Oh yeah, set up a filter.
You can set up a mailbox or something and say, don't bother me with all the noise. When these 6 things come through, tell me.
Yeah.
And I thought that was a good price to offload that activity and use the CAN controller at 2515.
Yeah, that's it. Yeah, MCP 2515, I think it
And
is.
there's
Yeah,
a 2562, which I
that's the
might
interface.
no 51 is the interface,
Oh,
but the F and the XLs are 2562, 61, 62.
okay.
And I might just do that. That's got a 3-volt happy interface. The 2515 is one at 5
Oh,
volt
you
level.
could hook it right to the pins, but if you had any kind of ground bounce problems, you could get out of range really quick. So that those little, sub-dollar 8-pin interface ICs that give you at 3.3 volts RX and TX or whatever you want. Could be
Uh-huh.
1.8, 3.35. You set it with the VCC pin. And then on the other side, it has the CAN H and CAN L. Those are kind of hardened for the application. So I think in that case, just use one of it's kind of a good deal. Just buy that chip and listen to it.
Yeah.
And you don't need, because really to just listen for messages, there's only like 4 parts of a message. There's the ID arbitration, then there's the payload, there's a checksum, and then there's data if it was specified.
Yeah. Anywho, yeah, I do like CAN, and I'm glad there's an old version, like the USB 1.1. I'm glad there's an old version
Yeah.
we can use.
Yeah, USB 1.1 it's not super fast, but it's pretty straightforward.
It does the trick. Yeah, not screaming fast for my big storage, but I don't intend to be. I mean, a lot of the horsepower on these machines is just moving gobs of 4K data through video and stuff like that. When
Right.
I'd rather compact it and just send. Well, like you stepped away. I'm talking about. I send a vector stream to my video display. My HDMI stuff I showed just briefly a month or two ago. I want to get back to that and dial that up and give me a full, big, rich display, vector display. Well, I'll send it vectors, but it renders it
Right.
on the screen. Yeah, send the data.
Yeah, no, the seminal data is
Send
where
the
it's at.
instructions and
For a lot of cool stuff, you shouldn't need high bandwidth, but all these things get used, like you said, for sending 4K data and other junk, and
yeah,
then that's like stratospheric. But for control stuff, CAN at 250K baud is probably sufficient for potentially big complex things.
yeah. Yeah, it's a new world. No end to the fun here.
Yeah, I've personally,
And
I've
once I got
gotten,
embraced the hooking up multiple P2s and just now I say in a new folder, I say set yourself up, and it goes out and gets all the drivers and the debuggers and the builders and stuff. It does all the tool chain stuff. I don't ever touch it anymore.
Yeah. What were you saying, Ray?
oh, I found Modbus and I've decided I like it, and so I think it's good enough for everything I do. So I know there's the CAN bus and the Profi bus, and those things are probably a lot better. But for like the simple stuff I'm doing, Modbus is perfect. Yeah.
Yeah, I don't know. I've never done anything with Modbus. I don't know. I looked into CAN bus because Doug wanted to do something with it, but it's kind of CAN bus is cool in the way the arbitration works. It's like the
Yeah.
messages begin with IDs, and then and there's so on the CAN bus you have 2 wires, right? And at either end of the network they're pulled together with like 60 ohm, no, 120 ohm.
120.
resistance. You got 60 ohms total. So any transmitter's job is to pull those things apart by 2 volts. So CAN H goes a little high, CAN L goes a little low. And they're just a differential pair. So when they get pulled apart, that's a 0, right?
Oh, so CAN bus is also the physical layer. Okay. So
Yeah.
in
Yeah.
my bus, it's just TCP, and it's and or you can also have it
Oh,
as
okay.
just
So it's
serial.
Ethernet.
You can
You
have
can also have
Modbus
it.
ASCII, yeah.
You can also have a serial, and the serial you could make it RS-45 if you wanted to, but yeah. So
I
it's
see.
yeah. So it's
There
yeah.
is something I liked about it, working with it last year and getting into PLCs and the kind of it just kind of mirrors a whole stack of registers around the bus. So
Yes.
everybody can just I can just always look. I kind of can forget that I have to do something out there. The
Yeah.
Modbus is reloading these registers
Yeah.
all the time, so I just look locally at what I want.
Yeah. And then you do your handshaking over bits, like you'll drive one high, the other guy will respond, "Oh, I see it." Then you go low, then he goes low.
Yeah, the other
And
thing
then
I'm finding is that, like, at least in America anyway, that like everything you can buy, it will talk Modbus. Like even the fanciest stuff, the thousands of dollars stuff will talk Modbus. So you can, and the cheapest stuff won't talk some of these other protocols, but it'll talk Modbus. Some of them are just Modbus only. So yeah, so
Yeah.
for me
yeah.
anyway, Modbus is like a universal solution. I
Well,
mean,
because Modbus, it sounds like it uses Ethernet, right?
there's two versions. There's the one that uses Ethernet and one that's just a serial connection.
Okay. Okay.
They're kind of the format's more or less the same, but there's
Yeah.
slight differences. But yeah, there's this, but yeah, they're more or less the same.
The
There's some minor differences.
So I got to tell you, CAN bus, it's so cool the way this works. So you have these signals you can pull apart, right? And you can let go and they'll collapse back to no differential. So what happens is every message starts with an ID. So you got all these people on the Modbus that want to send their message, right? And they precede the message with their ID. So they're all watching the bus activity, so they know when the time is to send a new message. So all messages start with a 0. So it's like this, psh, spread the lines for a time period. Psh. Then you start giving the ID bits. Well, as soon as everybody asserts their ID bits in series, MSB to LSB. So as soon as someone, some guys are going to do this, some guys are going to do this, but this always wins because this is what's on the wire. So if you're going to output a 1, which is this, but someone else outputs a 0, you go, oh, give up this message because that guy's already, he's going to stay on because he's going to see his data being reflected properly on the CAN bus. If you don't see your data being reflected, then you wait for this message and you try again next time. So there's never any lost bandwidth on the bus. So everyone has to be kind of a good citizen where they don't just flood the bus with, message IDs that begin with contiguous zeros because those guys are going to win most of the time. So they have to be, just periodic. But this way, someone's going to get their message through. The guy that keeps seeing his state reflected through the ID, he knows that he's winning. He can then go ahead and do his data and other stuff. But if you were giving your ID out and you put a 1 and you saw someone drove the bus to 0, because everybody can drive the bus to 0. But if you see a conflict there, then you back off and you go, okay, not my turn, wait. So it's really simple the way the arbitration works. It's a really ingenious idea.
Yeah, the priority in the ID is the lowest value is the highest priority. The lowest number, so
Yeah.
you get you get a bunch of zeros.
Yeah. And a 0
And
is this. This is a 1. 1 is default. But see, everybody can drive a 0, but only if nobody's driving a 0 do you see a 1 on the bus. And this low baud rate, like these vehicles tend to use like 250K baud, which is not very high.
yeah,
So you get 4 microseconds per bit, which in a propeller is like an eternity,
Yeah.
But that's good enough for, signaling engine status and suspension stuff and, dash controls. All this stuff's
Blinkers, yeah.
on the CAN bus.
More in the engine stuff. They've got the faster CAN bus now, CAN types.
Right.
For that really high speed, more real time critical in the engine.
Well, they talk about going up to 8 meg, but I mean, are they still using like passive, resistors to pull the lines together at either end? Because
Yeah,
that works great at 4 microseconds per bit, but
right.
at 8 megahertz, it seems now you're going to get off into some other thing where you kind of have to you're going to have to actively drive the other state.
Yeah.
Then the beauty of the concept starts to get polluted.
But they still collecting license fees, so they can keep. That's illogical. Right. You can keep driving it however you need to keep adding next level. So you have to keep chasing them. But yeah, like I said, I'm glad the lower level ones are open now.
Right.
So CAN open. Well, speaking of that, I was in fact starting to cook up my own sync language between the devices, and then realized, well, CAN open has specified a lot of this stuff. A lot of it being what IDs make sense for certain things, and it sort of blocked out the prioritization of certain devices. And I said, I don't need to make that up. I'll go use that standard, whether I'm not going to go test probably for it, but if it's something that's pseudo compatible with all the other equipment out there, I might get another CAN open. Oh, you've already got a controller for this. It already speaks CAN open. I can blend that in and map it and control it.
Yeah.
And not have to be stuck with my own mapping.
Yep.
We'll try to get a circuit board together next time.
So were you saying it can actually work on the circuit board? You said it was getting the schematics together.
It's in two different schematic capture circuit board layout tools, KiCad and LibrePCB. I gave it a starter project, empty project, just so the bulk of the structure was already there. And it can read their text format, so they can read through and understand where everything is and start filling in the text to get the right parts into the schematic and hook up the nets, ground and the power nets, and some of the data pins are understandable, recognizable, and it hooks those up. And I told it, I'm going to lay it out, so don't worry about that. And I suppose once I get it done, I'm laid out the way I want, I'm going to say, well, I'll run the design rule checks, but I'll say bundle it up so I can package it, because that seemed to take me longer than laying out the circuit board, is getting all the right files packaged the right way for the right place to upload at the right time. Claude probably figures that out pretty quick now.
Mm-hmm. Yeah, I can manage details all right, as long as it doesn't forget things. But I think it's getting better at picking up loose ends. Like I was surprised when we asked it to look for the steering data and noticed that there were actually two IDs that it was coming across on with different frequencies. It's like, as an engineer, I might have just found the first one and go, well, this must be it.
Yeah. Yeah.
You know that
No,
this. Oh, go
I'm
ahead, Martin.
sorry, dumb question. Back to the can thing. I read about that years ago, and from my little bit of understanding, dummy that I am, of course, and smiling, is that it's similar to the I squared C, but it uses statistics with those weights you were talking about who's more important in what you got to look at. So a light being out is less important than the I'll say the oxygen sensor readings when it that kind of a thing, right? So it uses basically it's all statistics, right?
Well, you could, I guess you could qualify it like that, but it's really just kind of arbitration. So the designer has to pick IDs that match the intended priority. Like if you want to be, not rude and hog the bus, but you want to be sure to get your message through 10 times a second, then you could pick a high priority ID and it will
which is
probably
a
get
lower
through.
number,
Yeah. Turns out being a lower number. Yeah.
and
Yeah.
encode that in binary. So as bit comes out, the one that's got the lower numeric value, that their sequence of bits coming out in order will win the bus.
Yeah, so everybody has to pay attention. Did my value get reflected? And the where you back off is if you output a 1 and somebody else output a 0, that means that there's someone else who's winning the arbitration. So give up this packet, let it fall through, follow it so you know where it ends and everything. Then at the instance of the next packet, you can assert your codes until someone else wins because they put out a 0 or you put out a 1. But if you get all the way through your ID, having had success, then at that point you can know that you're the only one on the bus now that is in charge at this, because you've won the ID war. Now you can send your message, and everybody else was following what was happening, so they know how many bits are going to come across, and they can monitor it and see if, by the way, was a checksum right? And then did it get acknowledged by anybody later on? So, because there's a last bit where somebody asserts a 0 to say I got it, and it looks good.
Got it. Yeah. Yeah. I've been listening the whole time, and now I got it.
That's the kind of like I'll say similar to an act then in a way.
Kind of.
Yeah. Okay.
Yeah.
Okay, I get it.
Yeah,
Okay, I get it.
Yeah. So my crude understanding is that CAN bus and Profibus can help you when you have a lot of devices on the bus. And I guess it's mostly about this arbitration stuff. But I kind of wonder, like, why would you pick CAN bus over Profibus and vice versa? Because they seem pretty similar functionality wise.
So CAN bus over who bus?
Profibus.
Profi?
I guess. PROFI.
Well, because CAN bus was what was in cars. So that's where I landed on that. And I could find cheap breakout boards on Amazon. I didn't see cheap Profibus there.
Okay, I found it.
Oh, CAN bus is on cars. Okay, I get it. I think they use it for factory stuff too, but
yeah, they do more and more in machine control, and that's why I'm also wanted to marry up my own boards with that across the bench, for example, to map it all into one memory space effectively, seemingly, sort of in the way the RS-45 would too, but.
There are protocols that can ride on top of CAN bus like this. I think it's called J1939. That's what heavy equipment and off-road vehicles use also, as where they've standardized like certain motor ID messages, like here's the motor RPM, here's the fuel level, a few other simple things.
Oh, see. So I think I'm seeing it now. So CAN bus is what you want to use if you're doing something that with a motor involved, probably.
Yeah, it's used for automotive stuff, whereas Profibus is factory and process automation.
Yeah, the CAN bus monitors all of your since everything's fuel injected now, and you have all the sensors from the O2 sensor, this sensor, all those sensors, and and they do barometers and all that junk and everything. It runs through all that to make your engines a bit more efficient.
Yeah.
Okay, and so and it also deals with altitude and all that stuff. As we're like in the airplanes that I fly, I do all that manual, so it does it all with all the sensors.
Okay.
And so, unlike a carburetor in the real car days, where you have to rejet it, readjust it if you move from LA to Big Bear because you're now at 7,000 feet, okay, you'd be running rich up there, so you got to fix it, redo that if you're always there. And if you come back down, you got to rerun it, redo it because you'd be running lean. So it does it for you.
Yes. Well, yeah, the CAN bus can be used to send configuration data around. So CAN open, I'm looking up the difference here. CAN open is actually just a higher level protocol that rides on top
layer
of
on
CAN
top
bus.
and
Yeah,
convention to the
just like
mappings.
yeah, like J1939 is the heavy equipment one. I just asked OpenAI and it gave me like 2 columns, like here's CAN bus, here's Profibus, and then here's a bunch of criteria down the side. So
Yeah.
it answers each one. Yeah, but I like the CAN bus. It's just such a nice, clean, simple idea.
Do you Bosch owns CAN bus? Is it Freescale or Motorola? Somebody came up with Lin bus, tried a competitor back in the 90s. Supposed to be cheaper. I don't know, cheaper license or cheaper
Only the license would be
electrically.
less. I mean, electrically, CAN bus is about as well. So you do need. I mean, assuming the signals are getting far enough off ground that they're not going to be in a 0 to 3.3 volt window, you want that interface chip because it'll still. Well, no, even on signaling, actually, it takes, I think, 5 volts. So it pulls the lines apart and then it lets them rest. I think maybe all it has in it is just some hardening and a differential sensor. So it can let the lines float and then they should bias around midway of 0, like 2.5 volts, and then it can pull the lines apart and it can give you a differential 0 or 1 back. But I think it's just probably mainly hardening, beyond what you could do directly with the microcontroller is those CAN interface chips are just providing the hardening.
Uh-huh.
And the
yeah,
besides a
transceiver.
simple yeah. Well, yeah,
Again,
there's a
I
little bit of
thought,
transceiver function, but that's trivial, It's like, do you see 2 volts between the lines? If so, that's a 0.
yeah.
If not, return a 1, and then either pull them apart or let them go together. Anyway,
Hey guys, thanks. I had a lot of fun. Always a pleasure. I got to run.
okay, Martin, take care. We'll see you later.
Compare.
Okay, thank you. And Shannon, that was a lot of fun. Very interesting.
Yep. Oh, so hey, Shannon, this LLM
Yeah.
thing really intrigues me. Because I mean, this is like a really simple. I mean, the LLM concept is like it's out there, right? It's being used, but to see it in a very like I'd really be interested to know like for super simple data sets and training, whatever is comprised here, what can you do? Like it would be so cool to have like a little test bed, like, okay, if you want to have this much memory, this is what you can achieve. I don't know if you'd have tokens. I guess you'd have tokens, right? They're all gonna deal with tokens eventually. But it'd be so interesting to see like if you just think of it as a machine where you're going to ultimately converse in tokens and then you're going to have some training process and you're going to have some goals that are tied to the training process and you're going to wind up with this big matrix of weights, right?
Yeah.
and then the actual program is going to it's just going to run the same process every time
Yeah.
through. It's going to
Yeah.
be tokens in and tokens out, right? Is that what happens?
So,
Yeah.
so this, I mean, there's been a lot of convention and machinery built around how the TensorFlow stuff is working, how the models are built now. But this little neural net sort of thing has been done on raw hardware without all that.
Oh yeah, it's even an analog.
And, you know, years and years ago. And there were little voice recognition chips that will recognize a dozen words.
Right.
And it was, I mean, there's enough horsepower now that you can train on the whole chain of the analog signal. But I think, like you were looking at before in the phonemes around
Right. Yeah, if you could
words, there's a signature of these phonemes around the words that's how the neural nets got trained on a very
you need
reduced.
a formant detector is maybe kind of hard to build, but if you could do our ears are good at formant detection, but it's math wise that there's got to be a way to do it that's not too hard, but our ear seems really good at resolving things that are hard to at least I don't see normal math expressing, like an FFT is a very incomplete way to show what your ear sees because it's all binned out. And what if it was continuously variable? You see, then it's correct, right? So if you could feed formant data into like formant and voice and unvoiced data into a neural network, then it could resolve speech much better than if you just gave it raw samples. Because if you gave it raw samples and it was big enough and powerful enough and you could train it, it would actually wind up creating its own effective formant detector on its own front end. It would effectively create that through the general neural net solution. But if you could give it a leg up by doing that kind of simple stuff ahead of time and giving it meaningful information. The more meaningful information you can give it, the more efficient it can work.
Yeah, I've been looking into wake word detection and for example, and what I'm seeing is that they kind of do what I did. They look at FFT, they FFT it, and you window it, you FFT it.
Right.
Well, they take it to the next step. They pick out. I guess there's a set of certain frequencies they look at, and I forget the name of it, but there's a set. And then they FFT it again, and that's what they search on. To bat.
They're trying to do what your ear does automatically without any effort. It's not a direct. It's not a one-step process using conventional math.
There's like it's built into these browser chat things now, kind of a notch filter around frequencies that a voice won't be. If it's in those frequencies, your voice isn't making it. It just takes those out.
Right.
And reduces the set of data it has to process.
It's pitch. See, pitch is like a one-dimensional way to describe what is actually what your ear sees as a complex curve. Like let's say you have an instrument and it's doing 440 A, 440 hertz A, right? Well, it's the shape of its harmonic patterns define its timbre and everything, right? Even though the pitch could be constant. And that's how our voice is. The vocal tract shaped creates the timbre because it's augmenting some harmonics and attenuating other harmonics, but in like a flowing pattern. And so that's what you need to do, have machines understand speech. You have to make some kind of system that gives them some kind of timbral shape, not just let it look at the pitch lines and try to.
Yeah. No, I think the problem. Yeah, I think that picking those certain frequencies is kind of getting rid of the timber. I think that's the idea there.
Uh,
What it wants, and then, but the problem is like, even I looked at even my speech. When I say a word, the main frequency will change during the day. You know, if I do it once, it'll be someplace. I do another place, and that's why you do FFT on the FFT. So you're looking at
yeah,
like
that would tell you the pitch. That's a pitch
patterns.
detector. Yeah, that's an
Well,
FFT of an FFT would be a pitch detector
well,
because
it's more like it's the temporal evolution of pitches is what
yeah,
it's looking at.
that's what it's looking at.
So it's
Yes.
pitch versus it's looking at you do so basically you plot pitch versus way if your pitch, and then you match that, you try to match that to the input and to see if it's there or not. And in that way, if it's a woman or a man, totally different pitches, it'll still show up the same way.
Well, see, this is all the same pitch. Ooh, wow. That's all the same pitch, but different formant shapes, different formant presences, and even nasal attenuation. So that's the key to detecting words, is looking at the change on the pitch lines. Like if you can determine pitch, then what you can do is you can look at certain FFT bins and get the formant shape.
Yeah, well, that's what they do. There's a set of the thing is, this is all a done deal. I mean, the people figured it out
Yeah.
already. So, I mean, you don't have to invent it. It's done. Getting it to implement on a P2, that's where I think AI, because it's all in these things that right now we don't have a C plus. Well, maybe we do now have a C compiler. I'm not sure how it didn't work on some things when I tried it, but
Well, this
yeah.
is FlexSpin, right? Or is it Ross's compiler?
No, it's this LLVM thing. It's a new
Oh,
one.
yeah. LLVM, yeah.
So that, well, so I don't know, but maybe you don't need that if AI can just make regular C code out of it. But anyway, oh,
Or you
one
can
other
make
thing,
regular speed.
yeah, why not? Yeah, because the AI could probably just do spin just as easy as C, so why not?
Just now it does, yeah.
But the other thing you asked about LLM, and my understanding is LLM, once it's trained and everything, it's just matrix multiplication.
Yes, yeah.
So, and then the new thing is it used to be all floating point, but now they've made it for small devices, well, like your home computer, for example, or these ESP32s. They make it either 8-bit integer or 4-bit integer matrix multiplication, which is kind of interesting. Well, that's where the mol command and
Yeah.
P2 we finally have that. That's the thing that can make it work, right?
I was
discussing this with Claude last week and getting the LLM to work. Yeah, we were talking about the integer, and that was a huge asset to do it all in integer. And I think, in fact, well, I don't know. It seemed like other implementations were depending on their floating point hardware.
Yeah,
But
yeah.
I think you're doing it if you do the adjustment of the data ahead of time, so you can do it all straight integer, it comes out faster.
Yeah, that would make sense. I was reading that you can use 32-bit floats in these LLMs, but it's kind of overkill. And then floating point, the next step down is 16-bit, right? So floating point 16 normally has a 5-bit, it has a 1-bit sign, a 5-bit exponent, and then a 10-bit mantissa. That's 16 bits. But they have this other thing. For if you're going to have word size, instead of float FP16, they have FB, floating brain 16, where you actually have a 1-bit sign, a 7-bit exponent, and an 8-bit mantissa. So you get higher dynamic range and less precision. but they found that's way more effective for doing these kinds of
Yeah.
LLM type
I was just
operations.
I was just hearing that they just don't do floating point at all for small things, like even your own computer. They just
Yeah.
you don't use floating point at all. It's all integer, and you can it and like 8-bit is like the usual, but they also now have 4-bit if you want to get like.
Yeah.
But I don't
Yeah.
think 4-bit versus 8-bit, does that help you on a P2? I don't think so, right? So
No, yeah, 8-bit would be free. Even 16-bit would be free, I think. So we have 16 by 16 multiply. Yeah, well, yeah, integers obviously super simple and fast. See, it'd be so interesting to see, like, when you got that LLM running, I'd be very interested to see the code that makes up the engine. Like, does it look at the inputs and then run all this matrix stuff? Hey there, how's school? Runs all this matrix stuff and then outputs what is a token and then feeds that back in to some degree and then runs the process again and gets another token. I really wonder, like, what is the procedure? Because it'd be interesting to know that, because it'd be so cool to have like a little test bed. Like, okay, if we're going to make like a it'd really be neat to know at various levels, various degrees of finiteness, what can be achieved, because I don't have any metric in my head for how that would work.
yeah,
But it'd be,
I don't know how it works either. If it does it because I think it's either one letter at a time it feeds in. I mean, because there's an input, there's a matrix multiplication, and there's an output. And
yeah. Well, yeah, and
so
that thing about feeding
I'm
letters in.
imagining it.
Well, go
Yeah, I'm
ahead.
imagining it's feeding letters in, but it could be maybe it's feeding whole words. I don't know.
Well, I would think it would certainly be, just think about it. It would be way more effective if you gave it the words, right? Like if you parsed the words ahead of time. See, this is where making front ends and back ends can really help the center part, the neural net become way more effective, is that you give it the most meaningful data. So you would then parse the string coming in, figure out this word code is 5. So here's a 5. That word code is 6. So here's a 6, and otherwise you're going to need a much bigger uh, matrix, and it's going to have to effectively build that through inference in itself. But if you could just take care of the really obvious stuff at the front end, then you can get by with a much smaller LLM, a much smaller neural network. You know what I mean?
Yeah, I think I've told you. I think I've just said the limit of my knowledge on that subject. So
Well, the good thing, who can explain this would be any of these AIs. They could probably.
Yeah.
And I
I'm
started looking into
just
it one
going in.
day.
I had to jump over to another machine that has the code on it. I'm now just looking more at it. It's as it was training things, it went through a variety of model implementations, a test code, and ended up at the REPL, supervisor data, DSL, and then REPL, the command line. And demo. I said when I went away, I didn't have time. I posted this in the forum too, I think. I was in a hurry and I didn't have time to launch it up and write it stuff myself. Give an example of using it.
So
I
it might have
said,
done overkill.
Grammar Walker. Oh, here's cogs all laid out. This is the top to bottom. This is PASM. Cog, that's the 0 cog. Cog 1. Oh, worker cog. It's got 3 of these that's doing the multiplication. Attention cog. And element-wise cog. And scheduler cog. And that's what's in here. PASM and those chunks broken out. But I've got a whole other overview doc too that we explains what's going on. Honestly, I didn't come back and look at it yet. The Unified Implementation Plan. This is it learning how it wants to use the integer. There's no floating point. And the Q exponent, Q log, fixed point. And there's a concept of fixed point encoding that it uses a lot through everything I've been doing the past few months. I should study more and understand it.
What's it called? You said six what?
Fixed point encoding. Well, that's part of using where you put the decimal point. How I've taken all these floating points and I multiply them all by some amount to force the decimal place off and have all integers. But the amount you multiply by and then divide on the other side there's terms for 4.6 and 8.4 and different 5.27 fixed point. Something to look up. And here's how it's going to record it. It's going to use it for this. And if you read fast, in and out of hub RAM. Don't be bothered by the PS RAM. The FIFO per cog. I guess it's just learning all the gotchas for how to make use of the features. Topology. That's topology up at the hardware level where I've got two P2s. One's the LLM and one is the expert system, the rules and facts. Settle design decisions. Got a whole thing section here. And don't relitigate this because it's sorted it out. Don't think about it again. Just do it this way. Cog budget. Drivers are cogs. There's cog 0, the role, supervisor, serial link driver, the flash file system driver, the PS RAM driver. Oh, no, that's on idle. That's the boot setup. And then once we load on the inference stuff. The supervisor is the tokenizer detokenizer, the grammar walker, and the capability mask and phase management as it shifts through the roles on all these cogs. Serial link scheduler is the orchestration of the ISA interpreter. Scalar stages, a bunch of algorithms. And the masked argmax, that's an algorithm thing that it seemed quite happy that it discovered that it should use here. And then there's 3 workers. And then the attention, the scores, the online softmax. And then element-wise, on the end, is bundling stuff up. So pipelining anyway, it sort of is in that order. Where the first 3 cogs chain the stuff together, dump it into a big pile, 3 cogs in the middle, grind through the pile, cast it out, and then 6 and 7 do other stuff in a pipeline. But this phase inference, that phase management at cog 0 has an inference action where it queues up the cogs in different roles, and the phase U is the model update where it's reloading a different model. So maybe it's already doing that shift in model stuff I was talking about. Maybe I just load another inference model on top of this process. Oh, numeric design, formats, tensors, weights, activations, accumulators, KV cache, norm weights, attention scores. Attention scores are Q8.24 fixed point.
Wow.
Yeah, so it's going right to town on blocking out RAM and bytes and bits and divvying it up in different chunks.
Let's see. I asked when we were doing this, I asked ChatGPT about trying to come up with some graph of like, and I'll show you a graph here that it made. It's kind of maybe worth seeing. Let's see. Okay, so I asked it, you know, about this BF16 is brain float 16. Anyway, so I said, what about a 20 word vocabulary? And it said, okay, so with 20 words, you could have these kinds of conversations. Whoops. And so that's already, there's a bunch of buried concepts in there, but it ultimately came up with this graph. This is kind of good news. So see, here's the complexity. Here's the percent effectiveness on the vertical, and then the number of parameters, yeah, going off on the X. So look, by the time you even hit here, I mean, it climbs exponentially. Then it starts to like smooth, kind of like a logarithm, it smooths out. But I mean, with 100,000 parameters, you're at like 82 versus for 1,000,000, you only get to 95. So you could do 30,000 parameters, you get 68. 82. So there's a point of diminishing return, which is always, so that's where you'd want to be. You want to be at the inflection point, right?
Right. Let me see if I can pull out what it said about that. Specifically, scaling table. Oh, okay, yeah. The integer pipeline estimates scaling table. So if you had vocabulary of 512 words, 90,000 parameters, is a 50K blob of data. Stores that 90,000 parameters.
You're talking about nibbles? 90,000 nibbles?
Kilobytes.
Oh, okay.
And it fits easily in the hub. Estimated tokens per second. Running the P2 at 200 megahertz estimates for 512 word vocabulary about 150 tokens per second. So think of that as characters coming out.
Right.
Faster than you need at that. So the next step, 2048 words, vocabulary, 2048 words. There's 1.1 million parameters. But those parameters are, not whole bytes. There's a relationship between the bytes, because that 1.1 million parameters stores in a 350K blob. Easily fits in hub RAM. And so that's where we landed, I think. And it said the target was 30 to 75 tokens per second. Certainly easy to work with. I ended up getting 90 tokens a second.
Okay. And did you
And
see them
2,000
coming?
words is way more than I realized. I'd forgotten. And I didn't go pick these words. It went through the
It
student
made all those
documentation,
decisions.
the smart pen documentation. What kind of words are we going to use around smart pens? And went out from there and pulled in its own corpus of words to train on, which maybe I could find those words in, must be stored in here
So
somewhere.
it did 2,000 words, huh?
Yeah, yeah.
And that because Claude just figured, well, I think this is going to be good. So it did 2,000 words and it filled up probably most of the memory, right?
350K.
And it was
That's
giving,
the blob of the weights that it needs to access really fast for all the multiplication stuff.
yes.
So that left what 150K for program code that's running on a variety of cogs and in HubRAM. But so yeah, like you were saying, not a lot of code.
Yeah. Yeah, it's just a thing. So it's interesting to know what steps does it have to go to produce one token. So it seems like there's a couple little steps and it's pipelined them by using different cogs. But it may not be getting good utilization because some of those cog processes, I mean, it's only going to be as fast as the slowest one, right?
Well, I mean, it went back and forth on what got done on what cog. Some of it, timeline wise, I mean, pipeline wise, had to be in a certain order. I mean, not numerically cog wise, but
Right.
some of the activities had to live on separate cogs and run in a pipeline. I mean, it could, and I said use everything you need to use. And in fact, they're not all. I mean, some of these are just the serial, some orchestration things and one is the PSRAM driver, which I don't think we ended up using at all. So that's a whole cog that could come back for other application stuff.
Yeah. Interesting.
Let me see if I can find that your data corpus pi. Sounds good. Okay. It's a couple pages of here's some examples of the normal syntax that it wants out. It's got a whole bunch of those. And quote, set up UART transmit on pin curly P at curly B baud, end quote. Or quote, configure serial output on pin curly P at curly D baud.
Wow.
Or down lower, quote, listen for serial data on pin P at baud. Or quote, measure the frequency on pin P over T U, unit, over time and unit. So in these curlies here, apparently that's code to insert what word you detected or insert what word you want into those slots.
Yes.
Yeah. So there's
but it's going to be flexible as you speak to it. If you didn't word it exactly like that, it would know what you're talking about, right?
Right. This is the output. This syntax here, these words in this order are what my limited language accepts as real.
Okay.
But I can ask it in different orders. And let me see if I can find one of the examples of it asking it in an odd order and getting it shifted around right.
It's almost like you want to fill a few variables in and then give it a verb.
Upload again, packet, 7. Let's see. Here's my weights.bin is 185,000 bytes, 185K is my weights. Come on now. Look at that demo one. Here. Fun. Fun.
Fun? You're having fun?
You have fun. I'm having fun. All of that. Banner.
If Grammy settles down, we're just gonna hit her
Okay.
in a little bit.
Yep. Yeah. Here's a couple phrases it's stuck in there. Yeah. In English, count edges on pin 12 for 10 seconds. Set up UART transmit on pin 20 at 115-200 baud. Generate 25 kilohertz PWM on pin 9 at 40% duty.
That's crazy. That's pretty
If
neat.
pin 5 goes above, here's a good one. If pin 5 goes above 900, turn off pin 33. Read pin 7, turn off pin 14. Sample analog voltage on pin 40. Measure the frequency on pin 3 over 2 seconds. Use pin
Wow.
16 as a mailbox register.
So that's pretty good. 185K can coordinate all those activities. Not coordinate, but kind of like, well, yeah, I guess it has to come up with some procedure in your language of what it wants to have happen, right?
I think it might run through all of those accepted. The ones I was reading before, all of these are acceptable patterns of output. And it might run through the LLM and dump out a bunch of patterns that might or might not fit the patterns, acceptable patterns. And it might say, oh, if we spit something out, it doesn't fit a pattern here. Or we spit one out, and let's just look at all the acceptable patterns. Oh, it must be this one, and insert the value and pass that out. I don't know. That's how I do it. I don't know what it's done, but I think that, the training, when you're training neural nets, and I've been training neural nets, I haven't jumped in this giant TensorFlow stuff, but just in the old days, in the 90s, in college and stuff, I was doing neural net stuff. And give it, here's a whole series of inputs. Every character there, or say a word, is an input. It maps to an integer. And you run through the training data until you get it to map to one of those outputs, one of those accepted outputs. And keep training it until it ends up matching correctly, and then capture those weights and hold them again and again and again. So,
but what about values? The values are separate from the structures, right?
Seemingly, there's placeholders. I don't know how it does
that. I guess we don't need to know.
I used to care, but when this started working in 6 hours, I just kept running with it.
I understand. Okay, hey, I should probably get going. I gotta get over um to Doug's today. We got a bunch of parts in. We got to try out some stuff. Um, now the kids are here, they can watch my mom.
Yeah, I'm upstairs at mom's. I'm the full-time caregiver here.
Hey,
So
we
that was
got
my
this.
wife who just came by, covered me downstairs while their food was
Yeah,
going
yeah.
on.
I thought I heard something about that. So you and I have the same job. We got my mom, I'm going to turn the record off here. I'll just tell you. So stop recording. Okay. Yeah.